Orion's belt appears as a faint blur in the night sky. Just below it lies one of the most remarkable and active regions in the universe, known as the Orion Nebula. This nebula is not just a cloud of gas, it is an enormous region where new stars are forming. Within it, gravity draws together dust and gas, heat and radiation shape young stars, and new celestial bodies continue to emerge. This ongoing process is taking place approximately 1,300 light-years away from Earth. If observed through infrared instruments, it would reveal many stars being formed inside a dense cloud that preserves the same kind of material from which our own sun once originated. So, settle in as we journey far into the universe and all the way to the Orion Nebula. The Orion Nebula is a vast and glowing cloud of gas and dust in our Milky Way galaxy. It lies just below the three bright stars that form Orion's belt, in the constellation known as Orion the Hunter. To the naked eye, it appears as the middle star in the sword that hangs below Orion's belt. But when viewed through a telescope, that star is revealed to be an enormous shining nebula, one of the brightest and most beautiful objects in the entire night sky. This nebula shines with an apparent magnitude of about 4, meaning it is visible even without a telescope, especially on clear nights. It is located about 1,344 light-years away from Earth, making it the closest region of massive star formation to our planet. The nebula itself stretches roughly 25 light-years across, which from our point of view gives it an apparent size of about 1 degree, about the width of 2 full moons side by side. Its total mass is estimated to be around 2,000 times greater than that of our Sun. In older books, astronomers often called it the Great Nebula in Orion, or simply the Great Orion Nebula. The Orion Nebula is one of the most studied and photographed regions of the heavens. Scientists have observed it in detail for centuries, using everything from early telescopes to modern space observatories. Within its glowing clouds, astronomers have discovered much about how stars and planets are born. The nebula contains swirling disks of dust and gas that are slowly forming into new planetary systems. These are known as protoplanetary disks. It also contains brown dwarfs, which are failed stars too small to shine brightly, as well as powerful streams of radiation from nearby massive stars that shape and illuminate the surrounding gas. Even people who live in cities filled with artificial light can still catch a glimpse of this wonder. To the naked eye, it appears as a slightly fuzzy star in Orion's sword, while binoculars or a small telescope reveal its cloudy structure and gentle glow. The centre of the nebula shines brightest, while its outer regions fade into a soft bluish haze. The whole area seems alive with colour. Reds, blues, greens and purples blending together like the brushstrokes of a cosmic painting. At the heart of the Orion Nebula lies a small cluster of young stars called the Trapezium cluster. It gets its name from the shape formed by its 4 brightest stars, which are packed within a space about 1.5 light-years wide. On clear nights with good viewing conditions, 2 of these stars can even be seen to have smaller companion stars, forming 6 in total. These are all extremely young and powerful suns, only a few million years old. The Trapezium is part of a much larger group called the Orion Nebula cluster, which holds around 2,800 stars within a region 20 light-years across. Surrounding all of this is the enormous Orion Molecular Cloud Complex, a giant region of gas and dust that stretches hundreds of light-years and covers much of the Orion constellation itself. About 2 million years ago, the Orion Nebula cluster may have given birth to several fast-moving stars, including AE Aurigae, 53 Arietis, and Mu Columbi. These runaway stars are now racing through space at more than 100 kilometers per second, heading away from their birthplace. Observers often notice the nebula's unique greenish colour, which mixes beautifully with its red and blue tones. The red light comes from hydrogen gas glowing at a wavelength of 656 nanometers, while the bluish light comes from the reflection of energy given off by massive, hot, O-type stars in the nebula's centre. The green glow puzzled astronomers in the early 20th century because it did not match any known chemical element at the time. Some even believed it was caused by a mysterious new substance they called nebulium. But later, as scientists learned more about atomic physics, they discovered that the green light actually comes from oxygen atoms that have lost 2 electrons. These atoms produce a special kind of glow called a forbidden transition, which can only happen in the quiet, almost empty environment of deep space, something impossible to reproduce on Earth at the time. There is even a fascinating link between the Orion Nebula and ancient mythology. Some researchers believe that the Mayans of Central America may have described it in their story of the three hearthstones, a symbol of creation. In this myth, the three stones are thought to correspond to three bright stars, Rigel, Saiph, and Alnitak, which form a nearly perfect triangle in Orion. At the centre of this triangle lies Orion's sword, where the nebula itself glows like burning embers in a cosmic fireplace. To the Mayans, it represented the smouldering fire of creation. Even today, the Lacandon Maya still call it the smoke from sacred incense rising to the heavens. Surprisingly, the nebula was not mentioned by early astronomers like Ptolemy or the Persian scholar al-Sufi, who described other cloudy patches in the sky but not this one. Even Galileo, who observed Orion with his telescope in the early 1600s, made no note of it. This has led some scientists to think that the stars lighting the nebula may have grown brighter over time. The first recorded observation of the Orion Nebula as a cloudy, glowing region was made by the French astronomer Nicolas Claude Fabry de Peiresc on November 26, 1610. Using a refracting telescope purchased by his patron, he noticed that the star in Orion's sword was actually a fuzzy cloud of light. The first published account came later, in 1619, from the Jesuit mathematician Johann Baptist César of Lucerne. He described the nebula in a book about comets, comparing its misty light to the bright comet he had seen the year before, in 1618. His words mark the beginning of centuries of fascination with one of the most awe-inspiring sights in the entire sky, the great and glowing heart of the Orion Nebula. Long ago, when astronomers were still learning how to map the heavens, a few of them turned their telescopes toward a mysterious glowing patch below Orion's belt. One early observer described the stars at its centre as forming a rectangle, unlike the round head of a comet. He could not have known that he was describing what we now call the Trapezium cluster, a small group of young, brilliant stars at the heart of the Orion Nebula. The first person to see three of the four main stars in this cluster is believed to have been Galileo Galilei, who recorded them on February 4, 1617. Though he did not yet know what he was looking at, his observation marked one of the first human glimpses into this star-forming region. Over the next few decades, other astronomers also discovered the nebula, even though it could already be faintly seen with the naked eye. Among them was Giovanni Battista Hodierna, who made a sketch of it that later appeared in his book De Systemate Orbis Cometici, Dece Admirandis Coeli Caracteribus. Then, in 1659, the Dutch scientist Christian Huygens published the first detailed drawing of the nebula's central region in Systema Saturnium. For centuries afterward, the Orion Nebula would often be called the Huygens region in his honour. More than 100 years later, on March 4, 1769, Charles Messier observed the nebula and noted the trapezium stars as well. When he published the first edition of his famous catalogue of deep sky objects in 1774, the Orion Nebula became number 42 on his list, known ever since as Messier 42, or simply MM42. In the early 19th century, John Herschel began a grand survey of the entire sky. Between 1834 and 1838, he observed and charted the Orion Nebula from the southern hemisphere, using a private telescope 21 feet long near Cape Town, South Africa. His careful maps helped astronomers understand the nebula's true size and structure for the first time. By the mid-19th century, new tools began revealing even more secrets. In 1865, English astronomer William Huggins used his new spectroscope to study the light from the nebula. He found that it was made of glowing gas rather than countless distant stars, a major discovery that changed how scientists viewed nebulae. On September 30th, 1880, Henry Draper made the first ever photograph of a nebula, using an 11-inch telescope and a new dry plate process. His 51-minute exposure captured the ghostly glow of the Orion Nebula in more detail than any human eye could. Just a few years later, in 1883, another astronomer named Andrew Ainslie Common took even longer exposures, up to an hour, with a homemade 36-inch telescope in his backyard in West London. His pictures showed for the first time faint stars and details invisible to the naked eye, opening a new era of astrophotography. The new century brought more discoveries. In 1902, Vogel and Eberhard found that different parts of the nebula moved at different speeds. By 1914, astronomers in Marseille confirmed that the nebula was not still but rotating and swirling with irregular motion. Later, Campbell and Moore used the spectrograph to show that the gas was turbulent, filled with fast-moving currents and waves. In 1931, astronomer Robert J. Trumpler studied the stars around the Trapezium and realized that they formed a cluster. He named it the Trapezium cluster and calculated its distance to be about 1,800 light-years, 3 times farther than scientists had believed at the time, yet surprisingly close to modern measurements. The arrival of the Hubble Space Telescope in 1993 brought the nebula into a new age of study. Hubble's sharp eyes revealed the nebula in stunning detail, allowing scientists to build 3-dimensional models and observe protoplanetary disks, the dusty rings where new planets are forming. They also study how powerful ultraviolet light from massive stars shapes and sometimes destroys these young worlds. In 2005, Hubble's advanced camera for surveys completed the most detailed image of the nebula ever made. Over 104 orbits, it captured light from more than 3,000 stars, including newborn brown dwarfs, small dim objects that never became full-fledged stars. The following year, scientists discovered a pair of eclipsing brown dwarfs within the nebula, known as 2MASS J 05-35218 40546085. They orbited each other every 9 8/10 days, and strangely, the heavier one shone less brightly than its smaller companion. Centuries after Galileo's first glimpse, the Orion Nebula continues to surprise us. In October 2023, astronomers using the James Webb Space Telescope, JWST, found something extraordinary: pairs of free-floating planets the size of Jupiter, wandering together without a parent star. They were named Jumbios, short for Jupiter Mass Binary Objects. Then, in July 2025, JWST and ALMA telescopes together captured an even rarer sight: a planet forming directly from the swirling disk of gas around a young protostar called HOPS 315. Normally, these early stages of planetary birth are hidden behind thick clouds of dust, but by chance, a gap in the material allowed scientists to witness the very beginning of a world's creation. The Orion Nebula spreads across a wide area of the night sky, covering about 1 full degree, roughly the size of 2 full moons placed side by side. It is not just a glowing cloud, but a complex and active region filled with neutral gases, thick dust, shining stars, and glowing clouds of ionized gas. Some parts reflect starlight like a mirror, forming what are known as reflection nebulae. But the Orion Nebula itself is only one small part of something far grander: the Orion Molecular Cloud Complex. This enormous structure stretches across the entire constellation of Orion and includes many famous regions, such as Barnard's Loop, the Horsehead Nebula, Messier 43, Messier 78, and the Flame Nebula. Together, these clouds form one of the most active star-forming regions in our galaxy. New stars are being born everywhere within this great complex, but many of the youngest ones are crowded together in dense clusters, like the one that lights up the Orion Nebula itself. Astronomers now understand that the Orion Nebula is made up of an ionized region of gas, known as an H2 region, centered roughly on a brilliant young star called Theta 1 Orionis C. This hot, massive star lies on the side of a long, stretched-out molecular cloud. Its intense radiation has carved out a hollow cavity in the surrounding gas. Theta 1 Orionis C gives off 3 to 4 times more ionizing light than the next, brightest nearby star, Theta 2 Orionis A. Inside this glowing H2 region, the gas reaches scorching temperatures of around 10,000 Kelvin, but it cools rapidly near the nebula's edges. The beautiful light we see from Earth mostly comes from photoionized gas glowing along the back wall of this great cavity. Around this bright region is a dense, curved bay of cooler, more neutral gas. Within it lie thick clumps of material, and beyond it lies the outer edge of the giant Orion molecular cloud. The gas inside this cloud is far from still. It moves and swirls with great turbulence. Some parts shift at speeds of up to 10 kilometers per second, while others show local variations as fast as 50 kilometers per second or even more. Observers who have studied the nebula closely have given poetic names to its many striking features. The dark curve that stretches down from the north into the bright central region is known as the Sinus Magnus, or Fish's Mouth. The glowing areas on either side are called the wings. Other visible shapes have been named the Sword, the thrust and the sail, showing just how alive and full of character this nebula appears through a telescope. The Orion Nebula is a true stellar nursery, a cosmic cradle where stars are being born. Scientists have identified around 700 young stars at different stages of development within it. In the year 1979, astronomers using the Lallement electronic camera at the Pic du Midi Observatory discovered 6 tiny bright points near the Trapezium cluster. They believed these to be small, partly ionized globules being lit up from the outside by the nebula's radiation. Later, radio observations with a very large array revealed that these bright spots were actually compact regions about the size of our solar system. The new idea emerged that they were small, young stars surrounded by disks of gas and dust, disks that were slowly evaporating under the nebula's intense light. In the year 1993, the Hubble Space Telescope confirmed this theory by revealing over 150 such disks, now known as proplyds, short for protoplanetary disks. These are the earlier stages of planetary systems in formation, much like how our own solar system began billions of years ago. The large number of these disks in the Orion Nebula suggests that the creation of planetary systems may be a common process throughout the universe. Stars are born when clumps of hydrogen and other gases in an H2 region are pulled together by gravity. As these clumps collapse inward, they grow hotter and denser. The inward pull of gravity turns into heat energy, raising the temperature to extreme levels. When it becomes hot enough, nuclear fusion begins in the center, igniting a new star known as a protostar. This young star reaches a balance when the outward pressure of its light and heat stops further collapse. Surrounding the newborn star, some of the remaining gas and dust forms a wide, flat disk, the protoplanetary disk, from which planets, moons, and other bodies can eventually form. Observations in infrared light show that the disks in the Orion Nebula contain dust grains that are sticking together and growing larger, marking the early steps in the creation of planetesimals, the building blocks of planets. As time passes, the protostar becomes stable and enters what is called the main sequence phase, meaning it is now a fully developed star. However, the strong radiation from nearby massive stars poses a challenge to these fragile disks. Normally, such radiation would destroy any disks that form too close to the powerful Trapezium stars, yet many proplyds are found right next to this group, suggesting that these massive stars are actually much younger than the older stars surrounding them. Once new stars are formed, they begin to blow out powerful streams of charged particles known as stellar winds. The strongest of these winds come from massive or very young stars, far stronger than the solar wind from our own sun. When these winds crash into the surrounding gas, they create shock waves that push, twist, and sculpt the nebula into new shapes. These same shock waves also help trigger the birth of even more stars by squeezing nearby gas clouds until they collapse under their own gravity. Inside the Great Orion Nebula, scientists have found 3 different kinds of powerful shock waves, each one showing how wild and energetic this region truly is. Many of these shocks appear inside objects called Herbig Haro objects, which are bright spots where young stars are shaping their surroundings with bursts of energy. The first kind, called bow shocks, happen when 2 fast streams of particles crash into each other. They often appear near the hottest stars in the nebula, where fierce stellar winds rush outward at speeds of thousands of kilometers per second. In the outer edges of the nebula, these winds slow down a little, moving at only a few tens of kilometers per second. Bow shocks can also form at the front of powerful stellar jets, when those jets slam into the interstellar gas that floats between stars. The second type, known as jet-driven shocks, are created by narrow jets of gas that shoot out from young, forming stars known as T Tauri stars. These jets race through space at hundreds of kilometers per second, and when they hit slower gas around them, they form bright shock fronts that glow in visible and infrared light. The third kind, called warped shocks, look a bit like bow shocks to an observer, but they are formed in a slightly different way. They appear when a jet-driven shock runs into a stream of gas moving sideways, creating a bent or curved wave-like pattern. All of these shocks stir up the gases of the nebula, creating ripples and waves. Some of these waves are thought to be caused by a physical process known as the Kelvin-Helmholtz instability, which happens when fast-moving gas slides past slower-moving layers, creating rolling patterns that look like waves in the sky. The motion of the gases inside the Orion Nebula, also called Messier 42, is very complicated, but most of it seems to be flowing outward through an open region called the Bay and moving in our direction. Behind the glowing ionized region of the nebula lies a large area of cold, neutral gas, which is now slowly shrinking under its own gravity. There are also astonishing bullets of gas racing through the hydrogen clouds of the nebula at supersonic speed. Each one of these bullets is enormous, about 10 times wider than the orbit of Pluto, and the tips of these bullets shine brightly in infrared light because they contain glowing iron atoms. Astronomers believe these bullets were created about 1,000 years ago by a mysterious and violent event, perhaps the explosive birth of a massive star. Clouds like the Orion Nebula are common across galaxies such as our Milky Way. They begin as huge, cold, dark clouds made mostly of neutral hydrogen mixed with small amounts of other elements. Such a cloud can contain hundreds of thousands of times the mass of our Sun and stretch across hundreds of light years. The gentle pull of gravity tries to make the cloud collapse, but this force is balanced by the faint pressure of the gas inside it. When something disturbs this balance, like a passing spiral arm of the galaxy or the shock wave from a nearby supernova, the atoms inside the cloud start to combine into heavier molecules. The cloud then becomes what scientists call a molecular cloud, marking the beginning of a new cycle of star formation. Within about 10 to 30 million years, parts of the cloud reach a critical mass known as the Jeans mass, where gravity wins over pressure and the gas begins to collapse. As these regions fall inward, they flatten into spinning disks. The centers of these disks become new stars, and the leftover material around them can form protoplanetary disks, the birthplaces of future planets. This is exactly what is happening in the Orion Nebula right now. It is a vast nursery of stars still in the process of creation. The youngest and brightest stars we can see there today are thought to be less than 300,000 years old, and some might be as young as 10,000 years. Many of these newborn stars are massive and hot, pouring out strong ultraviolet light that ionizes the gas around them. The famous Trapezium cluster, located at the nebula's heart, is one example of this brilliant group of young stars. Over time, the intense ultraviolet radiation from these massive stars pushes away the surrounding gas and dust through a process called photoevaporation. This gradual clearing has carved out the great hollow space we see at the center of the nebula, allowing us to look deep into its core from Earth. Eventually, the most massive of these stars will burn out quickly and explode as supernovae. In about 100,000 years, most of the nebula's gas and dust will be blown away completely. What remains will be a sparkling open cluster, a collection of young, bright stars surrounded by delicate filaments of gas and dust, the beautiful remnants of the cloud that once gave them life. Things inside the Orion Nebula seem to be burning, as if the heavens themselves have caught fire. Shades of deep red, glowing blue, and misty green swirl together, painting a cosmic masterpiece that looks like an oil painting splashed across the night sky. But these colours are not just beautiful. They tell a story written in the language of chemistry and light. Every hue, every glow, is a clue that reveals what is happening within this vast cloud of gas and dust. So, what exactly makes the Orion Nebula shine so brightly, while most other clouds in space remain dark and hidden? The answer lies in a fierce and energetic process called ionization, set off by some of the youngest and most powerful stars in the region. At the center of this glowing cloud lies a small but incredibly bright cluster of stars known as the Trapezium cluster. These stars have only recently begun to burn hydrogen in their cores through nuclear fusion, marking their birth as true stars. Among them, one stands out above all others, Theta 1 Orionis C, a true giant. This star is dozens of times more massive than our Sun and shines thousands of times more brightly. It releases a constant flood of ultraviolet radiation so powerful that it fills the nebula like an invisible storm. The Orion Nebula itself is packed with hydrogen gas, the simplest and most common element in the universe. When the ultraviolet rays from stars like Theta 1 Orionis C strike these hydrogen atoms, they hit them with such force that the atoms lose their electrons completely. Neutral hydrogen, H, becomes ionized hydrogen, H+. This violent separation of particles is like lightning at the atomic level. Eventually, those free electrons don't stay away forever. They find their way back to the hydrogen nuclei. When they reunite, they release tiny packets of energy called photons, which are particles of light. These photons appear in very specific colors, forming the glowing spectrum that gives the Orion Nebula its famous pinkish-red shine. This process is called recombination radiation, and the red light most often seen is called the H-alpha line, which glows at a wavelength of about 656.3 nanometers. But red is not the only colour in this cosmic light show. Other elements are glowing too. Oxygen atoms, for example, can become energized twice, giving off a cool greenish-blue hue. Sulfur adds deeper shades of red. Each colour represents a different element and a different level of energy, allowing astronomers to read the nebula's chemical makeup like a glowing map of elements. However, the light does not spread evenly across the nebula. The regions closest to the Trapezium cluster shine the brightest because that's where the ultraviolet radiation is strongest. Farther away, the radiation becomes weaker, and the gas gradually returns to a neutral state. This creates a layered structure, with hot, glowing gas on the inside and cooler, darker gas farther out. The edge between these zones is called an ionization front, a moving boundary where the nebula is constantly changing shape. Over time, the radiation from the central stars blows away the surrounding gas, carving and reshaping the nebula, like a sculptor working with a light instead of tools. The bright areas we see are the results of this ongoing battle between creation and destruction. The star's light both reveals and reshapes their birthplace, exposing new pockets of dense gas where more stars may soon be born. What makes the Orion Nebula especially fascinating is that it changes in ways we can actually observe within a human lifetime. While most cosmic structures evolve over millions of years, astronomers have noticed visible changes in the Orion Nebula over just a few decades. Images taken years apart by the Hubble Space Telescope show moving knots of gas, shifting shock fronts and glowing edges that alter shape over time, like a living cloud, breathing and transforming before our eyes. Yet, the same ultraviolet light that creates this breathtaking beauty can also destroy. The radiation that makes the nebula shine can strip away the gas around newborn stars, erasing the material that could have formed planets. In this way, the Orion Nebula is both a cradle and a destroyer, a place where stars are born and planetary systems may be lost before they even begin. To the naked eye, though, the Orion Nebula's glow is faint. We cannot see most of its brilliant colours because human eyes are not sensitive enough to the deep reds and subtle blues emitted by the gases. The vivid images we see from telescopes are made using long-exposure photography and special filters that capture light our eyes were never designed to see. That doesn't make those images false. They are truthful, scientific translations of real light, revealing the nebula's hidden beauty. If we could somehow see it the way a powerful telescope does, the Orion Nebula would appear like a vast cathedral made of stained glass, glowing from within, a living monument to the power of light, radiation, and creation in the cosmos. If you imagine the Orion Nebula as a great cosmic womb, then at its very centre lies its powerful glowing heart, the Trapezium cluster. In the middle of this vast cloud of gas and dust, packed tightly together, there is a group of young, enormous stars whose energy dominates everything around them. Their heat, light, and radiation are what make the nebula come alive. Without them, the Orion Nebula would be nothing more than a cold, dark cloud drifting silently in space. But because of the trapezium, it burns and glows like a great furnace, alive from the inside out. The cluster gets its name from its 4 brightest stars, which form a rough trapezoid when seen from Earth: Theta, 1 Orion A, B, C, and D. These stars are incredibly young, only a few million years old. In the lifespan of the universe, that makes them newborns, but there is nothing weak about them. They belong to the O-type and early B-type classes, the hottest and most energetic kinds of stars known. Their surfaces can reach temperatures above 40,000 Kelvin, shining as fierce blue-white lights that pierce through the nebula like torches in a storm. Among these stars, one stands above all the rest, Theta 1 Orion C. This single star provides nearly 90% of all the ultraviolet radiation that makes the surrounding gas glow. It is not just large, it is immensely powerful. Its stellar wind, a constant stream of charged particles, rushes through space at about 2,000 kilometers per second. That wind carves tunnels and cavities in the nebula, shapes glowing walls of gas, and sends shockwaves rippling outward like invisible explosions. But the Trapezium cluster is not made up of only 4 stars. Hidden within its dazzling glow are more than 700 young stars. Some of them can be seen in visible light, while others appear only in infrared images. They're all different in size, brightness, and stage of development. Some are still surrounded by rings of dust that might one day become new solar systems. Others are already erupting with jets of gas and magnetic storms. Altogether, they form one of the densest and most energetic groups of stars in the Milky Way. What makes the cluster even more fascinating is how unstable it is. All these stars are squeezed into a space only about 1.5 light-years across, smaller than the distance between our Sun and Alpha Centauri, the nearest star system. Because they are so close, their gravity constantly pulls and tugs in different directions, twisting orbits and even throwing smaller stars outward at high speed. Some of the runaway stars seen near the Orion Nebula may have been flung out of the trapezium like stones from a slingshot. These chaotic gravitational battles do not just affect the stars, they also shape the nebula itself. The fierce radiation from the trapezium blows great bubbles into the surrounding gas, creating hollow cavities and tunnels through which ultraviolet light escapes. These focused blasts of energy carve out glowing pillars, trace bright edges along the gas clouds, and can even start the birth of new stars by compressing nearby material. It is a cosmic chain reaction, stars giving birth to more stars. There is also something curious happening inside the cluster called mass segregation. In many star groups, the heavier stars gradually drift toward the center over millions of years. But in the trapezium, this seems to have happened very quickly. Astronomers are still trying to understand whether this was caused by the way gravity behaved when the cluster was forming, or if it was built that way from the start. Either way, the result is clear. The largest and brightest stars are packed tightly together in the core, ruling over the surrounding nursery of newborn suns. Even more captivating are the small disks of gas and dust circling many of these young stars, called protoplanetary disks, or proplyds. These are the building blocks of future solar systems. The intense radiation from the trapezium both shapes and erodes them, leaving behind teardrop-shaped shadows that stretch through the nebula. In high-resolution images, they look like delicate cosmic cloaks streaming in the solar wind, a strange mix of beauty and destruction. The trapezium cluster is more than just a sight to behold. It is a living laboratory. It shows what happens when stars form too close to each other, too fast, and under harsh conditions. Every flash of light, every ripple of radiation, and every infrared spark tells a story about creation and chaos. It may even offer clues about how our own sun once formed, born among giants, in the glowing heart of a storm. A proplyd, which is short for ionized protoplanetary disk, is a glowing disk of gas and dust that surrounds a very young star. It is a place where planets might one day form, but it is being slowly eaten away by strong radiation from nearby massive stars. These disks shine because they are being heated and ionized from the outside. Nearly 180 of these mysterious objects have been discovered inside the Orion Nebula, more than anywhere else in the sky. In fact, Orion is the only star-forming region close enough to Earth for astronomers to study such a large number of them clearly. The story of their discovery began in the year 1979, when astronomers using the Lallemande electronic camera at the Pic du Midi Observatory noticed 6 bright, compact sources of light near the Trapezium cluster, the brilliant heart of the Orion Nebula. At the time, scientists thought these glowing patches were partly ionized globules, small clouds of gas being lit up from the outside by the intense energy coming from the nebula itself, known as Messier 42. Later, new observations with the Very Large Array Radio Telescope revealed something more fascinating. These glowing blobs contained dense solar system-sized structures. This gave rise to the idea that they might actually be young, low-mass stars still surrounded by disks of gas and dust that were slowly evaporating under the fierce radiation of nearby stars. It wasn't until the year 1993 that the mystery was finally solved. Using the Hubble Space Telescope's wide-field camera, astronomers obtained crystal-clear images of these disks and officially named them proplyds. In the Orion Nebula, the proplyds usually appear in 2 different forms. Some glow brightly when they lie close to a powerful star, their gas and dust lit up by intense starlight. Others, farther away, appear as dark, ghostly silhouettes, shadows against the glowing clouds behind them, because their own dust blocks the light. Some even seem to be pushed or reshaped by waves of radiation that sweep through the nebula like invisible storms. The Orion Nebula itself lies about 1,500 light-years from the Sun, inside the same spiral arm of the Milky Way galaxy as our solar system, and it remains one of the most active nurseries of newborn stars known to science. Each proplyd is a potential cradle for new planets and smaller worlds called planetesimals. According to current models, whether such worlds form depends on several delicate factors: the chemical richness of the star and disk, the temperature, and the distance of the disk from the star. So far, our own solar system, with its 8 planets, 5 dwarf planets, and at least 5 groups of smaller planetesimal systems, remains the largest and most complex planetary system ever observed. Most proplyds, however, either form no planets at all or produce only one large system of planetesimals before their material is blown away. Proplyds have also been found beyond Orion. The Hubble Space Telescope discovered several in another star-forming region called NGC 1977, which currently holds the largest number of proplyds outside the Orion Nebula, with 7 confirmed examples. This was also the first case where a B-type star, known as 42 Orionis, was found to be responsible for the photoevaporation, the process of stripping away gas from the disk. In another young region, NGC 2024, astronomers identified 4 clear proplyds and 4 possible candidates. 2 of these were already being evaporated by the light of a nearby B-type star. These discoveries suggest that planet formation can be strongly influenced, or even interrupted, by radiation from neighbouring stars, sometimes within the first 500,000 years of a system's life. Later, the Spitzer Space Telescope revealed a different kind of proplyd, showing long, delicate tails made of dust streaming away from the disks like the tails of comets. In a region known as Westerhout 5, many of these dusty proplyds were found surrounding the star HD 17505. In these cases, the outer layers of gas have already been stripped away, leaving behind a tougher inner disk, a few to 10 astronomical units across, that might still hold enough material for planets to form. The proplyds of Orion and other star-forming regions are now understood to be young, low-mass stars surrounded by disks that are gradually being eroded by nearby giants. They are usually found within about 1/3 of a parsec, roughly 60,000 astronomical units, from massive OB-type stars. Their dusty tails can stretch from 1/10 to 2/10 of a parsec, or about 20,000 to 40,000 astronomical units. Astronomers have also proposed a more massive kind of these objects, called proplyd-like objects. These were first found in the cluster NGC 3603, and later in Cygnus OB2. The ones in Cygnus lie between 6 and 14 parsecs from the cluster's massive stars and have tails stretching from about 1/10 to over half a parsec, that is, 24,000 to more than 100,000 astronomical units in length. Some of these show evidence that the material around them is being lost faster than it can fall inward, while others still appear to be gathering gas. These discoveries suggest that even among the stars, the struggle between creation and destruction, between forming worlds and losing them, is a delicate and beautiful balance. Brown dwarfs are strange, in-between worlds, not quite planets, and not quite stars. They are heavier than the largest gas giant planets, but not massive enough to truly shine like real stars. Their weight is somewhere between about 13 and 80 times that of Jupiter, which means that while they are dense enough to glow faintly with heat and light, they cannot keep burning hydrogen like normal stars do. Instead, some of them give off a weak glow by fusing a heavier form of hydrogen called deuterium, which has both a proton and a neutron in its tiny atomic heart. The heaviest brown dwarfs, those that weigh more than about 65 times Jupiter's mass, can even fuse lithium, another light element, for a while. Astronomers classify glowing objects in space by their colour, or spectral type, which tells how hot their surfaces are. Brown dwarfs belong to the cooler end of this family. They range from type M, which has surface temperatures between about 2,100 and 3,500 kelvins, to type L, between about 1,300 and 2,100 kelvins, to type T, between about 600 and 1,300 kelvins, and finally type Y, which is cooler than 600 kelvins. Because they do not have the steady nuclear fires of true stars, brown dwarfs cool down as they grow older, slowly fading through these spectral classes over time. The name brown dwarf was chosen to describe a colour that lies somewhere between red and black, a dim and murky glow. In truth, Most brown dwarfs would not look brown at all if you could see them with your own eyes. Many would appear magenta, pinkish purple, or even a dull red, depending on their temperature. Unlike the layered structure of most stars, brown dwarfs are thought to be completely mixed inside, churning from top to bottom so that their gases stay uniform throughout. Scientists first imagined the existence of such half-formed stars in the 1960s, but it took until the year 1994 before the first definite brown dwarfs were discovered. Because their surfaces are relatively cool, they are very faint in visible light and mostly shine in the invisible infrared part of the spectrum. When astronomers developed better infrared detectors, they finally began finding them in large numbers, thousands scattered throughout our galaxy. The closest known brown dwarfs are part of a double system called Lumen 16, a pair of L and T-type dwarfs about 6.5 light-years, or about 2 parsecs, away from our Sun. That makes Lumen 16 the third closest system to us, after Alpha Centauri and Barnard's star. The idea of brown dwarfs was first proposed by the astrophysicist Shiv Kumar in the 1960s. At that time, he called them black dwarfs, meaning dark, substellar objects wandering in space that were too light to sustain hydrogen fusion. But this name caused confusion. Black dwarf already described a cold, dead white dwarf star, while red dwarfs were known to still burn hydrogen. Also, these new objects could glow visibly for a short time in their youth. For these reasons, other names were tried, Planetary and Substar among them. Then, in the year 1975, Jill Tarter, during her doctoral work at the University of California, Berkeley, suggested the now famous term brown dwarf. She chose it because brown seemed like a fitting middle colour between red and black, dim, dark, and dull, even if not literally brown. The term black dwarf is still used today, but it refers to a very different thing, a white dwarf star that has cooled so much that it no longer shines. However, even the smallest white dwarfs would need longer to cool to that point than the current age of the universe, so such objects almost certainly do not yet exist. Early studies of very low-mass stars suggested that if a star had less than about 7/100ths the mass of the Sun, or about 9/100ths for older metal-poor stars, it would never start normal hydrogen fusion. It would instead become a degenerate object, supported not by heat but by the pressure of its electrons. These stars that never truly ignite are what we now call brown dwarfs, sometimes nicknamed failed stars. Later, more precise calculations confirmed that the true hydrogen burning limit lies between about 7 and 8/100ths of the Sun's mass. By the late 1980s, astronomers learned that deuterium fusion could occur even in objects as small as about 13.5 times Jupiter's mass, and that dust clouds in their cool atmospheres changed how they looked and glowed. But finding these dim bodies was extremely difficult. They gave off almost no visible light, and the infrared instruments of that era were too crude to detect them clearly. Eventually, improved surveys began to change that. Astronomers searched in many ways, taking multicolour infrared images of nearby stars, looking for faint companions to known stars and white dwarfs, studying young star clusters, and measuring tiny wobbles in stars' motion that might reveal close companions. For many years, these searches found nothing certain. Then, in the year 1988, astronomers discovered a faint object orbiting the white dwarf star known as GD165. The companion, named GD165b, had a very red and puzzling spectrum, far cooler than any known red dwarf at the time. For nearly 10 years, it stood alone as a mystery until, in the year 1997, the Great 2-Micron All-Sky Survey, 2MASS, revealed many more objects with the same colours and traits. Today, GD165b is recognised as the first known example of a new class, the L-dwarfs. Its discovery marked a turning point. Still, astronomers debated whether GD165b was truly a brown dwarf or simply a very small star. The difference is subtle. Both can have similar brightness and temperatures. The key lies in lithium. Real stars burn their lithium quickly, in just a little over 100 million years, while brown dwarfs do not. So, if astronomers find lithium in the atmosphere of an old faint object, it is proof that they are looking at a brown dwarf, not a star. The story of brown dwarfs, the strange cosmic objects that are too big to be planets and too small to be stars, began to unfold in the early 1990s. In the year 1994, astronomers from the California Institute of Technology, Srinivas Kulkarni, Tadashi Nakajima, Keith Matthews and Rebecca Oppenheimer, working together with Samuel Durrance and David Golomowski from Johns Hopkins University, made a discovery that would change our understanding of the stars forever. They found what became known as the very first T-class brown dwarf. A year later, in 1995, this mysterious object was confirmed as a faint companion orbiting the nearby star Gliese 229 and was given the name Gliese 229b. Gliese 229b became one of the first undeniable proofs that brown dwarfs truly existed, standing beside another famous discovery from the same period, Teed 1. Both of these objects were confirmed in 1995 by the detection of a special fingerprint in their light, a faint glow from lithium at a wavelength of 670.8 nanometers. This was important because real stars destroy lithium in their cores through nuclear fusion, but brown dwarfs are not hot enough to do so. The presence of lithium therefore proved that these objects were not full-fledged stars. Even more fascinating was what astronomers saw when they studied Gliese 229b in infrared light. Its spectrum revealed a deep signature of methane gas at 2 micrometers, a feature that had, until then, only been seen in the atmospheres of giant planets like Jupiter or in the hazy air around Saturn's moon Titan. Methane does not appear at the scorching temperatures of real stars, so this clue showed that Gliese 229b was much cooler and fundamentally different. This discovery helped scientists recognize a new family of cosmic objects, T-dwarfs, cooler even than the L-dwarfs known before. Gliese 229b became the prototype for this entire new class. That same year, across the Atlantic Ocean, a team of Spanish astrophysicists, Rafael Rebolo, Maria Rosa Zapatero Osorio, and Eduardo Martín, made another groundbreaking discovery. On the 6th of January 1994, using an 80-centimeter telescope at the Teide Observatory on the Canary Islands, they captured the first images of an object in the famous Pleiades star cluster that they would later call Teide 1. Its light spectrum was recorded later that year in December with the powerful 4.2-meter William Herschel telescope on the island of La Palma. After careful study, the team realized that Teide 1 was not an ordinary star. Because it belonged to the young Pleiades cluster, scientists could estimate its age, distance, and chemical makeup with high precision. Using the most advanced computer models of that time, they found that Teide 1 had a mass of about 55 times that of Jupiter, give or take 15. This placed it clearly below the threshold where a true star can shine through hydrogen fusion. When they published their results in the scientific journal Nature on the 14th of September 1995, it made headlines. The front page declared, "Brown dwarfs discovered official." Teide 1 soon became the standard by which other brown dwarfs were compared. The team later used one of the world's most powerful telescopes, the Keck 1 in Hawa 2, to look for traces of lithium in Teide 1's atmosphere. In November 1995, they confirmed that the object still contained all the lithium it was born with, untouched by fusion. This provided conclusive proof that Teide 1 was indeed a brown dwarf, a body too cool and too small to ignite the nuclear fires that make a star shine. For a time, Teide 1 held the record as the smallest and faintest object ever directly observed outside our solar system. Since then, astronomers have discovered more than 1,800 brown dwarfs scattered across our galactic neighbourhood. Some lie surprisingly close to Earth, such as Epsilon Indi Bar and BB, a pair of brown dwarfs orbiting a Sun-like star only 12 light-years away, and Lumen 16, a binary brown dwarf system just 6.5 light-years from us. To understand what makes brown dwarfs different, one must look at how stars are born. Stars form when vast clouds of gas and dust collapse under their own gravity. As the cloud shrinks, it heats up through a process known as the Kelvin-Helmholtz mechanism. At first, the cloud can easily release its heat into space, but as it becomes denser, radiation gets trapped inside. The temperature and pressure in the center rise dramatically until nuclear fusion begins. The energy from these fusion reactions then balances the pull of gravity, creating a stable, shining star. However, if the collapsing cloud begins with too little mass, less than about 8% of the Sun's mass, or roughly 1/12, the temperature inside its core never becomes high enough to trigger hydrogen fusion. Instead, as the gas compresses, Electrons within the atoms resist being squeezed together too tightly. This creates what is known as electron degeneracy pressure, a strange effect explained by quantum physics. This invisible pressure halts the collapse before the object can ever ignite. The result is a brown dwarf, a failed star that glows faintly with the leftover heat from its birth and slowly cools over billions of years. In some rare cases, a brown dwarf might later gain enough material from a companion star to reach the mass of a true star, but even then, it may still fail to light its nuclear furnace. These quiet, dark wanderers remind us that the boundary between planets and stars is not as sharp as we once thought. It is a twilight zone of cosmic in-betweens, where nature experiments at the edges of starlight. Lithium is one of the most telling ingredients in the study of brown dwarfs. These strange objects, which are often called failed stars, usually contain lithium, while small stars almost never do. This is because real stars, even the smallest ones that can sustain hydrogen fusion, quickly destroy any lithium they were born with. Inside such stars, the temperature becomes so high that lithium-7 atoms collide with protons, producing 2 helium-4 nuclei. The heat needed for this reaction is just a little lower than the heat required for hydrogen fusion. Since small stars mix their material through convection, the lithium in their entire volume eventually disappears. Because of this, when astronomers see a lithium line in the light spectrum of an object, it is a strong clue that the object is a brown dwarf rather than a true star. This method is often called the lithium test. Brown dwarfs can be split into 2 kinds, those that are heavy enough to fuse lithium and those that are not. The heavier ones can burn their lithium during their youth, while the lighter ones keep it. Those with a mass greater than about 65 times that of Jupiter can use up their lithium by the time they are roughly 500 million years old. Heavier stars, such as our own Sun, may still have some lithium in their outer layers because those layers never get hot enough to burn it, and the material there does not mix deeply enough to reach the scorching core where lithium would vanish. However, such stars can easily be told apart from brown dwarfs because they are much larger and shine far more brightly. Unlike stars, brown dwarfs grow dimmer and cooler as they age. They do not have a steady source of fusion to keep them glowing. Very old brown dwarfs can become so faint that they are almost invisible. Some, when they have cooled enough, even develop atmospheres that contain methane, a gas that cannot survive in hotter objects. One famous example of this kind of methane-bearing brown dwarf is Gliese 229b. Stars on the main sequence, by contrast, reach a minimum brightness they can sustain thanks to steady nuclear fusion. This brightness is usually at least 1/10,000th that of the Sun. In the atmospheres of brown dwarfs, fascinating weather-like processes take place. For instance, in the later types of L-dwarfs, astronomers noticed that the spectral line of iron hydride, FeH, becomes weaker. This happens because iron clouds form in the upper atmosphere, reducing the amount of FeH gas and blocking our view of the deeper layers that still contain it. As the dwarf cools even further into the T-type stage, the fetch lines reappear since the clouds begin to thin or break up, allowing a view into the lower, warmer layers where fetch remains. Young brown dwarfs that fall between the L and T types, roughly from type L2 to T4, often show unpredictable changes in brightness. Scientists think this could be caused by cloudy weather, glowing hotspots, magnetic auroras, or unstable chemical reactions. The clouds themselves can be made of iron, or they can form in layers, with a lower thick iron cloud and an upper silicate cloud. These silicate clouds might contain minerals such as quartz, enstatite, corundum, or forsterite. However, it is still unclear whether silicate clouds are always present in young brown dwarfs. The Spitzer Space Telescope has detected silicate absorption features between 8 and 12 micrometers in many, though not all, L-dwarfs. More recently, the MIRI instrument on the James Webb Space Telescope has also found silicate absorption in the Planetary Mass Companion VHS 1256b. Another astonishing discovery is that some brown dwarfs may experience what could be called iron rain. In certain cases, droplets of molten iron form high in the atmosphere and then fall downward through convection. This peculiar phenomenon does not happen in normal stars. In the year 2013, astronomers actually imaged a patchy, iron-filled atmosphere around the brown dwarf known as Lumen 16b, which is part of a nearby binary system. Even cooler brown dwarfs, such as those of the late T-type, may have thin cloud layers made from exotic materials like chromium and potassium chloride. or sulfide compounds such as manganese sulfide, sodium sulfide, and zinc sulfide. For instance, one variable T7 dwarf seems to have 3 distinct layers: a top layer of potassium chloride clouds, a middle layer of sodium sulfide, and a deeper layer of manganese sulfide. If these clouds are uneven or patchy, they can cause the observed fluctuations in methane and water vapor absorption. At the coldest end of the brown dwarf family are the Y dwarfs, such as Ys. This object is so cool that its surface may be half covered by clouds made of sulfides and frozen water ice. Like stars, brown dwarfs are born on their own out of collapsing clouds of gas and dust. But unlike stars, they never become hot enough to ignite hydrogen fusion. Some drift alone in space, while others orbit around stars, sometimes following strange, elongated paths much like planets do. Interestingly, all brown dwarfs are roughly the same size as Jupiter, no matter their mass. The largest brown dwarfs, those between about 60 and 90 times Jupiter's mass, are squeezed tightly by the pressure of electrons, a quantum effect also seen in white dwarfs. The lighter ones, closer to 10 times Jupiter's mass, are instead supported mainly by electrical, Coulomb pressure, like planets. The result is that their sizes differ by only about 10 to 15%, even though their masses can vary hugely. Because of this, brown dwarfs and giant planets can look surprisingly alike, and it can be hard to tell them apart. Most brown dwarfs stop fusing anything quite early in their lives. Even the heavier ones cool down fast enough that after about 10 million years, they no longer carry out any fusion reactions. They can still emit faint X-rays and glow warmly in red and infrared light for a long time, until they eventually fade to planet-like temperatures below 1000 degrees Kelvin. The giant planets in our solar system, Jupiter, Saturn, Uranus, and Neptune, share some traits with brown dwarfs. Like the Sun, they are made mostly of hydrogen and helium. Saturn, for instance, is nearly as large as Jupiter, though it has only about 1/3 of its mass. 3 of the 4 giant planets, Jupiter, Saturn, and Neptune, give off nearly twice as much heat as they receive from the Sun, showing that they still have active interiors. All 4 have their own miniature planetary systems, complete with rings and numerous moons, much like stars have planets. The International Astronomical Union, often called the IAU, officially defines a brown dwarf as any object whose mass is greater than about 13 times that of the planet Jupiter. This number marks the lowest limit for an object to ignite a special kind of nuclear reaction called deuterium fusion, where a heavy form of hydrogen burns inside its core. Anything smaller than that, if it orbits a star or a stellar remnant, is usually classified as a planet. On the other end of the scale, an object needs roughly 80 times Jupiter's mass to begin burning ordinary hydrogen in a steady way, and this marks the upper boundary of what we call a brown dwarf. Anything heavier than that becomes a true star. However, not everyone agrees that brown dwarfs should be defined only by their mass. Some scientists believe it would make more sense to define them by how they form. In this view, brown dwarfs are the smallest children of the star-forming process, objects born from the direct collapse of gas clouds, while planets are born later inside disks of gas and dust that spin around stars. This difference in origin may be more meaningful than the strict numerical limits of mass and fusion. The universe has also revealed many puzzling discoveries that blur the lines between planets and brown dwarfs. One of these is a very cold, dim object named WISE-0855, and another is PSO J318.5-22. Both are thought to have masses below the 13 Jupiter threshold, which makes it unclear whether they are drifting planets that lost their stars or ultralight brown dwarfs that never had one. Other examples include planetary mass companions like 2M12, 07b, 2MASS J, 044, 144b, and OFF98b, which orbit brown dwarfs instead of stars. The 13 Jupiter mass boundary is not a sharp physical line. It is more like a convenient guide. Objects slightly heavier than this tend to burn most of their deuterium, while those slightly lighter burn only a small part of it. The exact amount of deuterium burned depends not only on the total mass, but also on the chemical makeup of the object, how much helium and deuterium it started with, and how many heavy elements it contains. These ingredients affect how thick its atmosphere is and how fast it cools, which in turn changes its behavior over time. By the year 2011, the Extrasolar Planets Encyclopedia was already including objects up to 25 times Jupiter's mass, explaining that there was no clear dividing line at 13 Jupiter masses when looking at actual observations. 5 years later, in 2016, this upper limit was raised to 60 Jupiter masses after new research showed that the relationship between mass and density did not reveal any sudden break near the old boundary. Other catalogues have their own rules. The Exoplanet Data Explorer lists objects up to 24 Jupiter masses, pointing out that the 13 Jupiter distinction is not very helpful, especially for planets that have rocky cores. NASA's Exoplanet Archive goes even higher, including any object with a mass, or a minimum estimated mass, of 30 Jupiter masses or less. Below the 13 Jupiter limit lies another fascinating group, the so-called sub-brown dwarfs, or planetary mass brown dwarfs. These bodies form just like stars and brown dwarfs through the collapse of clouds of gas, but they never become hot enough to start fusing deuterium. Some researchers prefer to call them free-floating planets, while others stick to the term planetary mass brown dwarfs, since they resemble both categories in different ways. Scientists often rely on the spectra, or the light signatures, of these objects to tell them apart from low-mass stars. Yet, to truly know what they are, one must also estimate their mass, which depends on both their brightness and their age. Brown dwarfs with similar masses tend to form in similar ways and are hot when young. Over time, they cool down and dim, which makes their mass harder to determine. An L-type brown dwarf, for instance, could either be an old and heavy one that has cooled over billions of years, or a young, lightweight one still radiating leftover heat. For Y-type brown dwarfs, this confusion is smaller since they stay relatively cool and low mass throughout their lives. For L and T types, however, age estimates are still important. Astronomers can guess the age in two main ways: by looking for features in the light that reveal youth, or by finding whether the brown dwarf moves through space together with a known star cluster, whose age is easier to measure. One example of the latter is the young system 2M1207 and its companion 2M1207b. By studying their motion and light, astronomers determined that they belong to the TW Hydrae Association, a group of stars about 8 million years old. This helped them estimate that the companion has a mass of roughly 8 Jupiter masses, just below the deuterium burning limit. In contrast, an older example is the system known as Coconuts 1, which pairs a brown dwarf with a white dwarf. The white dwarf's age was found to be about 7 billion years, providing an anchor for the system's history. Using precise distance data from the Gaia mission, scientists calculated the brown dwarf's radius, and, from that, its mass, around 15 Jupiter masses, with a small margin of uncertainty. These special kinds of brown dwarfs belong to a group called Spectral class M 5.5 or later, and astronomers often refer to them as late M dwarfs. Every brown dwarf of this M type is still quite young. A good example is Tida 1, which was the first brown dwarf of this kind ever discovered, an LP 94420, which happens to be the closest known brown dwarf of this same category. The M-type stars are the coolest in the old and well-known stellar classification sequence. What makes them stand out is the way their light behaves when passed through a spectroscope. Their optical spectrum is full of dark lines, or absorption bands, caused by molecules of titanium oxide and vanadium oxide in their atmospheres. These molecules absorb certain colours of light, giving M-type stars their characteristic appearance. However, astronomers eventually found something that didn't fit this pattern. There was a faint companion star called GD165b, orbiting a white dwarf named GD165, which strangely did not show any of the typical titanium oxide absorption features. When more objects like GD165b were discovered, scientists realized that they were looking at a completely new kind of celestial body. This led to the creation of a new category known as L dwarfs. Instead of being defined by the metal oxides, like titanium oxide and vanadium oxide, these L dwarfs are recognized by other chemical signs, emission bands from metal hydrides such as iron hydride, chromium hydride, magnesium hydride, and calcium hydride, as well as clear spectral lines from alkali metals like sodium, potassium, rubidium, and cesium. By the year 2013, astronomers had identified more than 900 L dwarfs, mainly through large-scale sky surveys like the 2-micron All-Sky Survey, 2MASS, the Deep Near Infrared Survey of the Southern Sky, DENIS, and the Sloan Digital Sky Survey. SDSS. Interestingly, the L class also includes the coolest stars that are still burning hydrogen, those having spectral types between L2 and L6, with masses greater than about 80 times that of Jupiter. If GD165b was the model for L dwarfs, then Gliese 229b became the prototype of yet another new category, the T dwarfs. These objects have a peculiar pinkish magenta hue. In the near-infrared part of the spectrum, L dwarfs show strong absorption caused by water vapour and carbon monoxide, but Gliese 229b is very different. Its spectrum is dominated by methane, a gas that on planets within our solar system is found mainly in Jupiter, Saturn, Uranus, Neptune, and on Saturn's moon Titan. Because of the presence of methane, water, and molecular hydrogen, the near-infrared light from Gliese 229b appears bluish. Its visible light spectrum also lacks the features of iron hydride and chromium hydride seen in L dwarfs. Instead, its red light is heavily affected by the wide absorption bands of sodium and potassium atoms. This striking difference led astronomer J. Davy Kirkpatrick to propose a completely new class, the T dwarfs, identified by the presence of methane absorption in specific regions of their spectra. By the year 2013, about 355 of these T dwarfs had been discovered. Later, astronomers Adam Bagassa and Tom Gabal developed refined classification systems for these mysterious objects. According to current theories, L dwarfs are a mix of both extremely low-mass stars and true brown dwarfs, while T dwarfs are thought to be entirely brown dwarfs, objects too small to sustain hydrogen fusion. Interestingly, because the green part of their light spectrum is absorbed by sodium and potassium, T dwarfs would not actually appear brown to the human eye but rather magenta, a kind of purplish pink. At first, astronomers could only detect nearby T dwarfs, but modern instruments have revealed them at incredible distances. Some T-class brown dwarfs, like Y0316 plus 4307, have been found over 100 light-years away from our Sun, while the powerful James Webb Space Telescope, JWST, has detected even more distant ones, such as Uncover BD1, located about 4,500 parsecs away. That is nearly 15,000 light-years. By the year 2009, the coldest brown dwarfs known had surface temperatures estimated between 500 and 600 kelvins, roughly between 227 and 327 degrees Celsius. These ultracool bodies, belonging to the spectral class T9, include CFBDS-J 005 9 10.9001140 01.3, Euless-J 133 55 3.45 plus 113005.2, and Euless-J 003402.77005206.7. Their light shows a distinct feature near a wavelength of 1.55 micrometers, which some astronomers, including Delorme and his team, believe is caused by ammonia gas. They proposed that this could mark the transition to a brand new category of even cooler brown dwarfs, called Y dwarfs, beginning with subtype Y0. However, other scientists have pointed out that this absorption feature could also come from water or methane, so the true definition of the Y0 type remains uncertain. When the James Webb Space Telescope turned its gaze toward the Y dwarf Y03595401, it managed to record the most detailed energy distribution ever observed from such a cold object. JWST's instruments examined light from 1 to 12 micrometers, and also measured brightness at 15, 18, and 21 micrometers. The telescope detected a wide range of molecules in the dwarf's atmosphere: water, methane, carbon monoxide, carbon dioxide, and ammonia. While earlier telescopes had seen traces of some of these molecules in both Y dwarfs and warmer T dwarfs, JWST was able to capture all of them together in one continuous spectrum. In this brown dwarf, methane was found to be the main form of carbon, but small amounts of carbon monoxide and carbon dioxide were also present. Ammonia, which is often hidden within water's absorption lines, was finally seen clearly by JWST, especially in the range between 5.5 and 7.1 micrometers, and at longer wavelengths from 8.5 to 12 micrometers. There was also a newly detected ammonia feature around 3 micrometers. In the year 2025, astronomers Kevin Luhman and Catarina Alves de Oliveira proposed something entirely new, a fresh category in the stellar classification system called Spectral Class H, where the letter H stands for hydrocarbon. Their discovery came from data collected by the powerful James Webb Space Telescope. While studying a star-forming region known as IC 348, they identified a surprising number of brown dwarfs with very small masses, many even below the limit needed for deuterium burning. What made these mysterious bodies stand out was a strange absorption line found at 3.4 micrometers, which matched an unknown aliphatic hydrocarbon. This unusual feature could become the defining mark of the new H-class. In the atmospheres of brown dwarfs, where hydrogen dominates, there exists a delicate chemical balance between carbon monoxide and methane. At high temperatures, carbon monoxide reacts with hydrogen molecules to form methane and hydroxyl radicals. These hydroxyl radicals can later react again with hydrogen, creating water molecules. The reverse can also happen. Methane can react with hydroxyl to form carbon monoxide and hydrogen. At high temperatures and low pressures typical of L-type brown dwarfs, this reaction favours carbon monoxide. At lower temperatures and higher pressures, typical of T-type dwarfs, methane becomes dominant, especially near the boundary between T and Y types. However, because the gases in a brown dwarf's atmosphere are constantly stirred, methane can sink to lower layers, while carbon monoxide rises from deeper, hotter regions. The carbon monoxide does not easily turn back into methane because breaking its carbon-oxygen bonds requires a lot of energy. This results in a chemical imbalance, or disequilibrium, in the atmosphere that astronomers can observe. The shift from L to T types in brown dwarfs represents the point where the atmosphere changes from being mostly carbon monoxide to being mostly methane. The intensity of vertical mixing can move this transition point to either higher or lower temperatures. This is especially important for large exoplanets, whose extended atmospheres and lower surface gravity push the L to T transition to cooler temperatures. For most brown dwarfs, this change happens around 1200 Kelvin, while the exoplanet HR 8799c, with a temperature of about 1100 Kelvin, shows no methane at all. The boundary between T and Y dwarfs is often placed at roughly 500 Kelvin, mainly because very few of these cold, faint objects have been studied in detail. Future observations with the James Webb Space Telescope and with the upcoming extremely large telescopes may greatly expand the number of Y dwarfs with known spectra. These extremely cold objects display strong features of methane and water vapour, and perhaps even hints of ammonia and frozen water ice. Scientists believe that a variety of factors such as clouds, metallicity, lightning, photochemical reactions, impacts, and even metallic catalysts may influence the temperature at which the transitions between L, T and Y classes occur. Young brown dwarfs are known to have low surface gravity because they are larger in size but less massive than older stars of the same spectral class. Astronomers use Greek letters to note this. Beta means intermediate surface gravity, gamma means low gravity, alpha means normal gravity and is often omitted, and delta stands for extremely low gravity. Objects with low gravity can be recognized by certain patterns in their spectra: weak calcium hydride, potassium, and sodium lines, but strong vanadium oxide lines. If an object has an unusual appearance, scientists sometimes mark it with the suffix pec, short for peculiar. This can indicate odd properties such as low gravity, low metal content, or the presence of two unresolved stars instead of one. The prefix SD, meaning subdwarf, is used for cool, metal-poor stars whose motions resemble those of ancient halo stars, rather than the younger stars in the galactic disk. Subdwarfs tend to appear bluer than their disk counterparts, while some objects with red colouring are interpreted as older bodies rich in dust rather than as low-gravity sources. Those with bluish near-infrared hues may be unresolved L and T binary pairs, although some, like 2MASS J 11,263,991-5,003,550, are single objects with unusually thin or large-grained cloud layers. Most of the energy given off by L and T brown dwarfs shines in the near-infrared part of the spectrum, between 1 and 2.5 micrometers. As these dwarfs cool from late M through L and into T types, their spectra grow rich with detail, showing everything from sharp atomic lines to wide molecular bands. These features shift depending on the temperature, gravity, and metal content of the object. Under such cool conditions, gases begin to condense, forming dust grains and clouds. The atmospheres of known brown dwarfs usually range from about 2200 Kelvin down to around 750 Kelvin. Unlike ordinary stars that maintain their warmth through steady nuclear fusion, brown dwarfs gradually lose heat over time. The heavier ones cool more slowly, while the lighter ones cool more quickly. There is also evidence that the cooling process slows somewhat at the L to T transition, near 1000 Kelvin. Observations of brown dwarfs show that their infrared light often brightens and dims over time, suggesting enormous fast-moving cloud systems. These clouds, made of exotic materials, may block the hotter regions beneath them, creating storms far more violent than those on Jupiter. On the 8th of January 2013, astronomers using NASA's Hubble and Spitzer space telescopes mapped the turbulent atmosphere of a brown dwarf named 2-mass J, 22,282,889 minus 43,001,026.2. The result was the most detailed weather map of a brown dwarf ever created, revealing enormous planet-sized clouds driven by fierce winds. This research opened the door to understanding not only brown dwarfs themselves, but also the complex atmospheres of planets beyond our solar system. In April 2020, scientists succeeded in measuring wind speeds on another nearby brown dwarf, 2-mass J 10,475,385 plus 21,242,334. They found speeds reaching as high as 1,450 miles per hour, faster than the strongest hurricanes on Earth. By comparing the changing brightness of atmospheric patterns with the internal magnetic rotation of the brown dwarf, they confirmed earlier theories predicting such violent winds. Scientists now hope this technique can be used to study the weather and atmospheric movements of other brown dwarfs and distant exoplanets. In recent years, astronomers have used special instruments called coronagraphs to block the bright light of nearby stars so they can spot faint companions orbiting them. Using this technique, they have detected dim objects around bright stars, including Gliese 229b. At the same time, powerful telescopes equipped with charge-coupled devices, or CCDs, have searched distant star clusters and found faint objects such as Tidy 1. Large-scale surveys that cover wide areas of the sky have also uncovered individual faint objects like Kellu 1, which lies about 30 light-years from Earth. Many brown dwarfs have been discovered accidentally during searches for planets orbiting other stars. The same techniques used to detect exoplanets, such as measuring light variations or subtle movements of stars, can also reveal brown dwarfs. In fact, brown dwarfs are generally easier to find because they are more massive and emit more detectable light and radiation. Brown dwarfs can also be surprisingly strong radio emitters because of their powerful magnetic fields. Observations at facilities such as the Arecibo Observatory and the Very Large Array have detected more than a dozen of these ultra-cool dwarfs, as astronomers call them, due to their very low temperatures and unusual magnetic properties. The radio signals they emit allow scientists to measure their magnetic field strength directly. Since the year 1999, X-ray flares have been detected from several brown dwarfs, suggesting that their magnetic fields shift and change over time, much like those of small stars. Even though brown dwarfs do not fuse hydrogen into helium in their cores as true stars do, they still produce heat from deuterium fusion and gravitational contraction, keeping their interiors warm and active. Inside, their material churns violently in what scientists call convection, and when combined with their rapid spinning, this movement helps create a tangled and powerful magnetic field near their surfaces. In the case of LP 944-20, the Chandra X-ray Observatory detected a flare produced by magnetic activity just beneath the brown dwarf's outer layers, where hot, electrically charged gas, called plasma, swirls around. Using NASA's Chandra X-ray Observatory, astronomers also detected X-rays from a low-mass brown dwarf located in a multiple star system. This was the first time a brown dwarf orbiting so close to Sun-like stars, specifically TWA 5a, was observed in X-ray light. According to Yoko Tsuboi of Chuo University in Tokyo, the X-rays come from the brown dwarf's coronal plasma, which reaches about 3 million degrees Celsius. Tsuboi explained that even though this brown dwarf has only about 1/50th the mass of our Sun, it shines just as brightly in X-rays, hinting that even giant planets might produce X-rays in their youth. The first brown dwarf ever found to emit radio waves was LP 944-20, which also emits X-rays. Roughly 5 to 10% of all known brown dwarfs have strong magnetic fields and give off radio signals. Based on models, astronomers estimate that there could be around 40 magnetic brown dwarfs within 25 parsecs of the Sun. Interestingly, the power of their radio emissions seems to stay about the same even when their temperatures vary. Some brown dwarfs may have magnetic fields as strong as 6 kilogauss, and their magnetospheres, regions of magnetic influence, might extend about 107 meters above their surfaces. Scientists are still not sure whether these radio emissions resemble those of planets or stars. A few brown dwarfs even produce regular radio pulses, possibly coming from their magnetic poles or from active spots on their surfaces. The periodic flipping of the radio wave orientation could mean their magnetic fields reverse direction from time to time, perhaps due to a magnetic activity cycle similar to the 11-year solar cycle of our Sun. The first brown dwarf of spectral class M found to emit radio waves was again LP 944-20, discovered in the year 2001. Later, in the year 2008, astronomers detected radio waves from 2 mass J00361591 plus 182110, the first brown dwarf of spectral class L to do so. Then, 2 mass J10475385 plus 2124234 became the first spectral class T brown dwarf discovered with radio emission. This last finding was particularly exciting because it showed that even brown dwarfs, with temperatures similar to those of giant exoplanets, can have strong magnetic fields exceeding 1.7 kilogauss. However, when scientists searched for radio waves from Y-type brown dwarfs using the Arecibo Observatory in the year 2010, they found none. Estimates of brown dwarf populations in our cosmic neighbourhood suggest there may be roughly 6 stars for every brown dwarf. A later estimate from the year 2017, based on the young and massive star cluster RCW38, suggested that the Milky Way galaxy might contain between 25 and 100 billion brown dwarfs, a number not far from the estimated 100 to 400 billion stars in the galaxy. In August of the year 2017, NASA's Spitzer Space Telescope studied how brown dwarfs vary in brightness at infrared wavelengths, revealing that their cloud layers are not uniform. Instead, large waves ripple through their atmospheres, much like those seen on Neptune and other gas giants, changing the thickness of the clouds and moving at different speeds, probably due to differences in rotation. Later, in August of the year 2020, astronomers identified 95 new brown dwarfs close to the Sun through the citizen science project Backyard Worlds, Planet 9. Finally, in the year 2024, the James Webb Space Telescope provided the most detailed weather reports ever gathered from 2 brown dwarfs. These two, known collectively as Lumen 16, were first discovered in the year 2013 and lie only about 6.5 light-years from Earth, making them the nearest brown dwarfs to the Sun. Webb's observations showed that both have stormy, turbulent atmospheres filled with silicate clouds, with temperatures ranging between 875 degrees Celsius and 1026 degrees Celsius. This means that winds on these worlds may be blowing hot grains of sand through their skies. Astronomers also detected the chemical fingerprints of carbon monoxide, methane and water vapour, revealing just how dynamic and exotic the weather can be on these mysterious failed stars. Brown dwarf pairs, known as binary systems, come in many forms, but those involving brown dwarfs of type M, L and T are relatively rare, especially when the main object in the pair has a very small mass. Astronomers have found that L-type dwarfs form binary pairs about 1/4 of the time, while for late T and early Y-type dwarfs, those between spectral types T5 and Y0, the number drops to roughly 1 in every 12 systems. Interestingly, brown dwarf binaries show a very particular pattern when it comes to the balance of their masses. The smaller and fainter the system, the more likely the two objects have nearly equal masses. For example, in binary systems where the main object is a regular M-type star, the companion can have a wide range of masses, but usually not less than about 40% of the primary's mass. In contrast, brown dwarf pairs often show a much stronger tendency for both objects to be almost equal in mass, with the companion typically having at least 70% of the primary's mass. The distance between the two objects also tends to shrink with lower mass. Binary systems with M-type stars generally have separations ranging from about 3 to 30 astronomical units. 1 astronomical unit is the distance between the Earth and the Sun. For brown dwarfs of types M and L, this distance usually peaks between 5 and 8 astronomical units, while for the cooler T 5 to Y0 dwarfs, the typical separation is around 2.9 astronomical units. One of the best-known examples of a brown dwarf pair is Lumen 16a and b, the closest brown dwarf system to the Solar System. It consists of 2 L-type dwarfs, the primary being of type L 7.5, and they are separated by about 3.5 astronomical units. The mass ratio of the pair, about 0.85, fits perfectly within the typical range for brown dwarf binaries. Scientists still do not know whether this same pattern continues with Y-type dwarfs, the faintest and coldest class of all. These are very difficult to study because so few have been found. In the year 2023, astronomers confirmed that WISE J0336-0143, a Y plus Y dwarf system, is indeed a binary. Using the James Webb Space Telescope, they measured a mass ratio of about 0.62 and a separation of less than 1 astronomical unit, less than the distance between the Earth and the Sun. However, because the sample size is so small, it remains uncertain whether this system is typical or a unique exception. By studying how brown dwarfs orbit each other, astronomers can directly measure their masses. For example, in the system 2-mass WJ 0746425 plus 2000321, the secondary object was found to have a mass equal to about 6% of the Sun's mass. This is called a dynamical mass measurement. Lumen 16, being very close to Earth, has also been studied to search for planets around it, but so far none have been detected. Another important discovery was the wide binary system 2M1101A and B, the first brown dwarf pair found with a separation greater than 20 astronomical units. This discovery challenged old theories about how brown dwarfs form. Many scientists once believed that wide brown dwarf pairs could not survive long or would be broken apart within 1 to 10 million years. But the existence of 2M1101A and B showed that such systems could indeed remain stable for long periods, contradicting the so-called ejection hypothesis. This older idea suggested that brown dwarfs were originally formed in multiple star systems, but were quickly ejected before they could gain enough mass to ignite hydrogen fusion. A more recent discovery, the wide binary W2150A and B, shows similar properties to 2M1101 but is older and located in a quieter part of the galaxy, far from crowded star clusters. The fact that it still exists today indicates that it must have survived all the gravitational disturbances in its birthplace. W2150 also belongs to the small group of L plus T binaries that can be directly observed with ground-based telescopes. Other famous examples include SDS SJ1416 plus 13A and B and Lumen 16. There are also peculiar brown dwarf systems such as 2-mass J05352184 -0546085, which is an eclipsing binary. In this system, one brown dwarf passes in front of the other from our point of view. Curiously, the smaller and lighter brown dwarf in this pair is hotter than its more massive companion, an unexpected result that challenges our understanding of how heat and mass interact in substellar objects. Brown dwarfs orbiting close to ordinary stars are extremely rare, especially at distances smaller than 5 astronomical units. This scarcity is known as the brown dwarf desert. Fewer than 1 in 100 Sun-like stars have a brown dwarf orbiting within about 3 to 5 astronomical units. A well-known example of a star-brown dwarf pair is Gliese 229b, the first T-type brown dwarf ever discovered. It orbits the red dwarf Gliese 229a. Other examples include TOI 1994b, a brown dwarf that circles its star every 4.03 days. The boundary between massive planets and low-mass brown dwarfs is still debated. The National Aeronautics and Space Administration's Exoplanet Archive classifies any object with a minimum mass of about 30 Jupiter masses or less as a planet if it meets other conditions, such as orbiting a star. However, the International Astronomical Union's Working Group on Extrasolar Planets defines planets as objects with a mass below 13 Jupiter masses. Brown dwarfs found orbiting white dwarfs are particularly uncommon. The first L-type dwarf ever identified, GD165b, is part of such a system. These combinations help astronomers determine both the age of the system and the brown dwarf's mass. Other similar systems include Coconuts 1A and B, estimated to be around 7 billion years old, LSPM J0055 plus 5948A and B, around 10 billion years old, SDSSJ 22255 plus 0016A and B, roughly 2 billion years old, and WD 0806-661A and B, between 1.5 and 2.7 billion years old. Some white dwarf-brown dwarf pairs are extremely close together and are known as post-common envelope binaries or PCEBs. Only 8 of these systems have been confirmed so far, one of them being WD 0137-349A and B. During the life of such systems, the brown dwarf was once engulfed by its companion when the star expanded into a red giant. Brown dwarfs with masses lower than about 20 Jupiter masses would not survive this event. They would evaporate completely. The lack of brown dwarfs closely orbiting white dwarfs mirrors the brown dwarf desert seen around ordinary stars. As these PCEBs evolve, they can become cataclysmic variable stars where the brown dwarf donates material to the white dwarf. Computer models suggest that most of these evolved systems, possibly up to 80%, have brown dwarf donors. One particular subtype, known as WZ Sagittae-type dwarf novae, often contains donor stars with masses right on the borderline between the smallest stars and the most massive brown dwarfs. An example is BW Sculptoris, a dwarf nova whose brown dwarf companion was likely once a normal star that lost so much material it became substellar. As the system loses mass, its orbital period shortens to a minimum of about 70 to 80 minutes before slowly lengthening again. Astronomers call such systems period bouncers. There may even exist systems where a brown dwarf has merged completely with a white dwarf. A dramatic example could be the ancient Nova CK Vulpeculae, which some astronomers believe might have been born from such a violent merger event. The earliest phase in the life of a brown dwarf is known as the proto-brown dwarf, or pre-brown dwarf stage. These are the small and faint cousins of young stars called protostars. In astronomy, they are sometimes classified as Class 0 or Class 1 objects. Another group of extremely dim cosmic bodies, known as very low luminosity objects, often called velos, are also believed to be early brown dwarfs. These faint objects shine with less than 1/10 to 1/5 the brightness of our Sun and are usually found inside nearby clouds where new stars are being born. By the year 2024, astronomers had identified around 67 promising proto-brown dwarfs and 26 pre-brown dwarfs. Back in the year 2017, there was only one known proto-brown dwarf linked to a large Herbig-Haro jet, a glowing stream of gas caused by powerful outflows from a young stellar object. This rare brown dwarf, named Merit 1701117, is surrounded by 2 disks, a pseudodisk and a rotating Keplerian disk. From this small but active brown dwarf bursts a striking jet called HH1165, stretching about 7/10 of a light-year into space and glowing mostly in ionized sulfur light. Brown dwarfs are formed in much the same way as stars. Like them, they are surrounded by swirling disks of dust and gas known as protoplanetary disks. One famous example is Char 110913-773444. These disks around brown dwarfs show many of the same features as those around young stars, which suggests that planets may also form around brown dwarfs through the process of accretion. However, because brown dwarfs have much smaller masses, the planets that might form around them would most likely be rocky, Earth-like worlds, rather than large gas giants. If a large planet were to pass directly in front of a brown dwarf from our point of view, it would block a noticeable portion of its light, creating a clear signal for astronomers to detect through the transit method. But since the region where planets form around a brown dwarf lies very close to it, the powerful tidal forces of the brown dwarf would greatly influence the orbits of any planets that form there. In the year 2020, astronomers working on the citizen science project Disk Detective discovered the closest known brown dwarf still surrounded by a primordial, or Class 2 disk. The object, officially called Wuxia J12037.79-78, 4508.3, shortened to W1200-7845, was recognized because it glowed unusually bright in infrared light. After careful study, scientists confirmed with a 99.8% probability that this brown dwarf belongs to a young moving group of stars known as Epsilon Chamaeleontis. Data from the European Space Agency's Gaia satellite showed that it lies at a distance of 102 parsecs, or about 333 light-years, from Earth, placing it within our local cosmic neighbourhood. A scientific paper published in the year 2021 studied disks surrounding brown dwarfs in several young stellar associations located between 140 and 200 parsecs away. These systems, only a few million years old, were found to have disks too light to form new planets in the future. However, there were signs that planet formation might have already begun at earlier stages. Evidence such as dust grain growth, dust settling, and a gradual decrease in disk mass indicated that these disks are evolving, possibly hiding newly formed planets inside them. In the Orion Nebula, astronomers found 2 brown dwarfs whose disks could be seen in absorption, and at least 4 disks that are being slowly evaporated by strong ultraviolet radiation from nearby massive stars. These evaporating disks are known as proplyds. One of them, called proplyd 181-247, which is either a brown dwarf or a very low-mass star, has a disk about 30 astronomical units wide and containing a mass equal to around 6 times that of Jupiter. Most brown dwarf disks are smaller than 40 astronomical units in radius. Yet, in the distant Taurus molecular cloud, astronomers using the Atacama Large Millimeter Array, often called ALMA, discovered 3 brown dwarfs whose disks are much larger, more than 70 astronomical units wide. These massive disks could potentially form rocky planets with masses greater than that of Earth. Some brown dwarfs are even known to keep their disks for surprisingly long periods, longer than a few million years. Such aged disks, lasting over 20 million years, are playfully called Peter Pan disks because they seem never to grow up. At present, the only known brown dwarf with a Peter Pan disk is the object 2-mass J02, 265658-53 27032. Another remarkable brown dwarf, Ch1109 13-773444, lies about 500 light-years away in the southern constellation Chamaeleon. Astronomers from Pennsylvania State University believe it may be in the process of forming a tiny planetary system of its own. They have detected a dusty disk that resembles the one that once surrounded our young sun billions of years ago. With a mass of about 8 times that of Jupiter, Ch1109 13-7734. 44 is the smallest brown dwarf ever found, and if its disk indeed gives birth to planets, it would become the smallest known object to host a planetary system. According to the International Astronomical Union's definition, established in August of 2018, a planet can orbit a brown dwarf as long as its mass is below 13 times that of Jupiter. The mass ratio between the planet and the brown dwarf must be less than roughly 1/25. This means that a planet with up to 3.2 times Jupiter's mass could orbit a brown dwarf of 80 Jupiter masses and still be classified as a planet. Likewise, an object with about half Jupiter's mass could orbit a brown dwarf weighing 13 Jupiter masses and still count as a planet. Some of the most fascinating planetary mass companions discovered so far include 2M1207b, 2-mass J, 04, 4144, and OFF98b. These massive bodies orbit their brown dwarfs at great distances and may have formed not through the gradual buildup of material, but by directly collapsing from clouds of gas, making them more like miniature brown dwarfs themselves. The first discovery of a close companion orbiting a brown dwarf was made using the radial velocity method. The brown dwarf, called Char H Alpha 8, was found to have a small low-mass partner orbiting just a few astronomical units away. With the companion's mass about 1/3 that of the primary, the system behaves more like a tiny double star pair than a planet-star system. Later, in the year 2008, astronomers detected another companion called EMOA 2007 BLG 192LB, the first planetary mass object found orbiting a brown dwarf in a tight orbit. Planets that form around brown dwarfs are believed to be carbon-rich and poor in water, making them very different from the blue, ocean-covered worlds we know in our solar system. In the year 2017, a scientific study using the Spitzer Space Telescope suggested that at least 175 brown dwarfs would need to be carefully observed to ensure a 95% chance of detecting at least one planet smaller than Earth by using the transit method. This technique looks for tiny dips in light as a planet passes in front of its host object. The powerful James Webb Space Telescope, often called JWST, is expected to be capable of spotting even smaller worlds than this. In our solar system, the orbits of most planets and moons usually line up with the rotation of the star or planet they circle. If a planet's orbit happens to align with the rotation axis of a brown dwarf or a planetary mass object, astronomers can calculate how likely it is that such a planet will pass directly in front of its host and be detected as a transit. For example, if one considers an object with an orbit similar to Jupiter's moon Io, the probability of such a transit can be calculated using a mathematical relationship based on the angle of inclination, specifically the cosine of 79.5 degrees divided by the cosine of the inclination angle. Measurements have been made for several brown dwarfs and free-floating planetary objects. One example is SIMP 0136, which has an inclination estimated at around 80 degrees, give or take 12 degrees. Even if we assume the lower limit of 68 degrees, this still gives a nearly 50% chance, about 48.6%, that a planet in a close orbit would pass in front of it as seen from Earth. However, scientists still do not know how common such close-orbiting planets are around brown dwarfs. Some evidence suggests that they may actually be more common around smaller and lighter objects, because the disks of gas and dust from which planets form tend to shrink as the host's mass decreases. In the year 2025, astronomers using the Very Large Telescope found strong evidence for a planet orbiting two brown dwarfs at once, a so-called circumbinary planet, moving in a highly unusual polar orbit around a system known as 2M1510. This remarkable discovery showed that planetary systems around brown dwarfs could be far more diverse than previously believed. Researchers have also explored whether planets orbiting brown dwarfs could ever be suitable for life. Computer models show that the conditions for habitability would be extremely strict. The habitable zone, the region where liquid water might exist, would be very close to the brown dwarf, especially for the cooler ones known as T-dwarfs, at about 5/1000ths of an astronomical unit. This narrow zone would also shrink over time as the brown dwarf cools, since these objects only burn for a short period, usually no more than 10 million years. To remain stable and avoid deadly tidal forces, any planet in such a zone would need to follow a nearly perfect circular path, with its orbit's eccentricity as low as 1 part in a million. Otherwise, tidal stress could create enough heat to cause a runaway greenhouse effect, boiling away any water and making the planet uninhabitable. Such planets would also be unlikely to have moons. Interestingly, as far back as the year 1984, some astronomers proposed that our own Sun might have a hidden brown dwarf companion, sometimes nicknamed Nemesis. It was imagined that this unseen object could disturb the distant Oort cloud, where countless icy bodies orbit the Sun, and occasionally send comets tumbling inward. However, with improved observations and modern data, this idea has now largely been dismissed. Deep in the heart of the Orion Nebula, one of the most spectacular nurseries of stars in the sky, something very strange and fascinating is happening. In the cluster known as the Trapezium, a glittering jewel box of young suns, the biggest and brightest stars are not scattered at random. Instead, they are tightly packed together at the very centre, like a group of powerful figures surrounded by chaos, while hundreds of smaller stars, brown dwarfs and swirling disks that are forming new planets dance around them in wide orbits. This strange pattern is not an accident. Astronomers call it mass segregation, and it is clearly visible in the Orion Nebula. But what does that mean? Mass segregation is a process that happens in star clusters when gravity gradually sorts stars by size and weight. The heavier ones slowly sink toward the middle, while the lighter ones get pushed to the outer edges. It's almost like shaking a jar filled with sand and pebbles. The big stones naturally settle at the bottom while the fine grains spread around them. In the same way, the gravitational jostling between stars acts like a cosmic version of billiards, where each encounter changes their speed and direction. Heavier, slower stars end up in the cluster's gravitational centre, while faster, lighter ones drift outward. What's truly remarkable about Orion is that this sorting seems to have happened very early, possibly even before the cluster was completely formed. Some scientists believe that the massive stars in the Trapezium were born in the centre, not drawn there over time. This idea, known as primordial mass segregation, suggests that the most massive stars formed right at the heart of the action, where gravity was strongest and conditions most extreme. Why does this matter? Because it changes how we understand star formation itself. If mass segregation begins from birth, it means that giant stars can only form in very special regions, the dense, central pockets of collapsing clouds where gravity's pull is at its deepest. In other words, the universe might be pre-programmed to create its largest and most powerful stars at the very core of star clusters. Take, for example, Theta 1 Orionis C, the most dominant star in the Trapezium cluster. This cosmic giant is about 40 times more massive than the Sun and shines with thousands of times greater energy. Surrounding it are other enormous O-type and B-type stars, each unleashing intense ultraviolet radiation, violent stellar winds and magnetic storms. Together, they shape and even tear apart their surroundings, both helping new stars form and destroying potential birthplaces by blowing away the gas and dust that other stars and planets need to grow. Because these massive stars form first and sink deep into the cluster's gravitational center, they also become the most destructive. Their energy can heat the gas, erode planet-forming disks, and carve glowing cavities into the nebula itself. In Orion, this influence can be clearly seen. The once smooth cloud is now flattened, torn, and illuminated by powerful radiation. The very landscape of the nebula bears the scars of these central giants, like cracks on a shell shattered from within. But why does this division between big and small stars happen in the first place? One possible explanation lies in dynamics. As a cluster evolves, stars constantly interact with one another through gravity. The heavier ones slow down and naturally fall inward, like stones sinking to the bottom of a pond, while the lighter ones are pushed outward. However, the Orion Nebula is extremely young, only about 1 to 2 million years old, so it might not have had enough time for this gradual process to finish. That's why many astronomers think that Orion's central giants were shaped by their initial conditions, the way the original cloud collapsed. Another fascinating idea is called competitive accretion. In this model, baby stars, called protostars, that form in the dense center of the cloud have more access to gas and dust falling inward. They grow rapidly, feeding on the available material like cosmic parasites with front-row seats at an endless buffet. Stars that form near the edges have less to feed on, so they stay smaller and grow more slowly. This uneven feeding frenzy naturally produces massive stars in the core, securing their dominance early on. The gravity of these giants then begins to rule the neighborhood. Smaller stars are pulled into strange stretched-out orbits, or even flung away entirely, becoming runaway stars or lonely brown dwarfs drifting through space. So, the mass segregation we see in Orion isn't a quiet or accidental pattern. It's a living, changing drama. The center holds the power, while the edges feel the consequences, and these cosmic hierarchies have real effects on the future of the nebula. Massive stars live fast and die young. Their brief but violent lives end in dazzling supernova explosions that can split the nebula apart, reshaping its very structure. Their radiation can evaporate protoplanetary disks, the very cradles of future planets, changing how and where new worlds are born. Over time, gravity and feedback from these titanic stars sculpt the entire region into a complex web of holes, filaments, and glowing walls of gas. The Orion Nebula is not a smooth or gentle cloud floating in space. It is wild, rough, and full of patterns that look almost alive. If you could drift close to it, you would see an enormous web of glowing curves, twisting vines, and towering peaks that seem as though some invisible sculptor carved them by hand. And in a way, that's exactly what happened. Only this artist is not human. The sculptor of Orion is radiation itself, one of the most powerful and violent forces in the universe. Blazing young stars buried deep within the nebula flood their surroundings with fierce ultraviolet light. This light doesn't simply illuminate the gas, it slices through it like a knife. The Orion Nebula is made of gas and dust, but this material isn't spread out evenly. Gravity pulls some regions together into thick clumps while leaving others thin and empty. When giant stars, like those in the famous Trapezium cluster at Orion's heart, ignite, they pour out enormous amounts of energy. Their radiation blasts away the lighter, more fragile gas, while the denser pockets manage to hold on, resisting the onslaught. Over time, This constant battle sculpts the nebula into haunting forms, glowing pillars, ridges, and fingers of gas that stretch for light years. Astronomers call this process photoevaporation. It happens when radiation heats the surface of dense clouds, making their gas boil away into the darkness of space. The result is breathtaking, vast columns of gas trailing away from the light source, their edges glowing where the radiation makes the gas shine. These structures can be several light years long, yet they survive only because they are slowly being destroyed. The Orion Nebula is filled with these features. Some rise like tall statues in a cathedral made of a light, while others twist like ghostly ropes or weave delicate webs across the cosmic canvas. These long thread-like filaments often connect several young stars together, tracing the hidden pathways where gas collapses and new suns are born. In some cases, these filaments even act like interstellar arteries, channeling material into the hearts of growing protostars, tiny embryonic suns gathering strength. And at the very tips of these pillars, something miraculous often appears, small, bright points of light. These are newborn stars bursting from their dusty cocoons. It is an astonishing paradox. The same deadly radiation that tears the nebula apart also sparks the creation of new stars. When ultraviolet light hits a dense clump of gas, it compresses it, squeezing it until it collapses under its own gravity. Destruction and creation dance together in perfect balance. One of the most famous sights in the Orion Nebula is the feature called the Orion Fingers. These are thin, glowing jets and filaments that shoot outward from what seems to have been a violent stellar explosion near the Trapezium cluster. Astronomers think this chaos was caused by a collision or close encounter between massive stars. The fingers stretch across several light years, showing how turbulent and alive this region truly is. It's not just sculpture, it's explosive art, painted with light and energy. Even the direction of these pillars tells a story. Nearly all of them point toward the Trapezium stars, like tall grass bending in a fierce wind. That pattern reveals the truth. The massive stars at the nebula's center are shaping everything around them. Every curve, every bright edge, every shimmering wisp is their handiwork, carved by invisible chisels made of light. With the sharp eyes of the Hubble Space Telescope and the James Webb Space Telescope, astronomers can now see this cosmic artwork in astonishing detail. They've spotted filaments casting long shadows where thick dust blocks the light, and razor-thin fronts where ultraviolet radiation meets untouched gas. Borders between destruction and safety. In some images, you can even see frozen ripples, shock waves captured mid-motion, like sound waves turned to stone. Each glowing edge and dark lane is a snapshot from a process that unfolds over hundreds of thousands of years. But hidden within these glowing strands lies the true heart of Orion, the seeds of new stars. Inside many of these filaments are dense knots of gas slowly collapsing into future suns. They are invisible to the human eye, but in infrared light they shine faintly, revealing that they are very much alive. Many scientists believe that this thread-like filamentary structure is not unique to Orion. It may be the universal pattern of star formation. Stars seem to be born not in isolation, but within great tangled webs of gas pulled thin by radiation and gravity. So when we gaze at Orion's glowing pillars and winding filaments, we are not just looking at something beautiful. We are witnessing an eternal struggle, the battle between radiation and matter, between destruction and creation. Every bright ridge is a scar left by light, every dark hollow a cradle for something new. The Orion Nebula is not just a place where stars live, it is a living story of how the universe destroys and creates at the same time, and that is what makes it magnificent. The Orion Nebula is one of the most dramatic battlefields in the cosmos, a place where light and matter clash endlessly. Across most of it, chaos rules. Great towers of gas rise and twist, waves of energy tear through clouds, and everything seems to be in turmoil. Yet, in one small corner of this storm, there is an eerie calm, a sharp and shining frontier where the fight seems to pause. This is the famous Orion Bar, a narrow glowing line where light and matter meet face to face. It is one of the most closely studied regions in all of astronomy, a natural laboratory showing what happens when starlight collides directly with interstellar clouds. If you could see it clearly, the Orion Bar would look like a glowing golden blade cutting across the heart of the nebula, shimmering beneath the brilliant Trapezium cluster, a group of massive young stars that shine with fierce ultraviolet light. But the Orion Bar isn't a solid object. It's what scientists call an ionization front, the dividing line between two very different worlds. On one side lies hot hydrogen gas, glowing with energy after being stripped of its electrons by the ultraviolet light from the Trapezium stars. On the other side lies the cold, dense molecular cloud, a region full of dark dust and uncharged gas, hidden from the harsh radiation. Between these two realms lies the bar itself, a razor-thin boundary where ultraviolet rays are absorbed, atoms get excited, and everything begins to glow. It's like looking at a cross-section of a cosmic wound, where the destructive power of starlight meets the fragile calm of shadow. Astronomers love the Orion Bar because it gives them a perfect view of what they call a photodissociation region, or PDR, a zone where light breaks apart molecules without fully ionizing them. In this tiny strip of space, we can see every stage of transformation, from fully charged hydrogen near the light to half-ionized gas in the middle, and finally to cold, untouched material deep in the dark. It's not only beautiful, it's a treasure of scientific information. The Orion Bar is so close to us in astronomical terms that it feels like slicing open a cake and seeing each layer inside. By observing it, astronomers can study how temperature, density, and the makeup of chemicals change across just a few trillion kilometers, a distance that sounds enormous but is tiny on a galactic scale. They use powerful instruments like the Very Large Telescope, VLT, on Earth, and space observatories such as Spitzer and the James Webb Space Telescope, JWST, to look into this delicate zone in incredible detail. What they have found is astonishing. The Orion Bar is only about 1/10 of a light-year wide, roughly 630 billion miles, yet within this narrow space, entire atomic transformations take place. Hydrogen atoms lose their electrons, carbon atoms become ionized, molecules of hydrogen are torn apart, dust grains heat up and begin to glow in infrared light. It is a rough, fiery region, a cosmic frontier where light and darkness wrestle for control. The bar also helps scientists understand the importance of dust. Tiny grains made of silicon and carbon act like shields, absorbing ultraviolet light and protecting the gas hidden behind them. How well these grains block the radiation determines how deeply starlight can pierce the cloud, and whether new stars can safely form in the shadows. If the shielding fails, the cloud gets eaten away. If it holds, new suns are born under its protection. But the story doesn't end there. The Orion Bar is also shaped by violence from nearby stars. Shock waves from stellar winds slam into it, squeezing the gas even tighter. These bursts of pressure can actually trigger the birth of new stars as clumps of gas collapse under their own weight. So, this thin glowing edge is both a record of destruction and a cradle of creation, a cosmic paradox where endings and beginnings exist side by side. Chemically, the bar is like a glowing jewel filled with signatures of life's building blocks. Gases like carbon monoxide, ions of sulfur and oxygen, and complex molecules known as polycyclic aromatic hydrocarbons, PAHs, all shine here when hit by starlight. By studying these glowing fingerprints, scientists can see how starlight changes the chemistry of space, how molecules are broken, reshaped, and reborn in the fire. It's like watching alchemy happen on a scale larger than imagination. The Orion Bar is not frozen in time. It slowly shifts and crawls inward as the Trapezium stars continue to burn, pushing their radiation deeper into the nebula. If you could speed up time, you would see the bar slowly devour the cloud layer by layer. In a few 100,000 years it will vanish, its gas consumed, its stars formed, its dust scattered to the winds. Yet for now, it remains one of the clearest dividing lines in the entire night sky. Not just between light and darkness, or hot and cold, but between theory and reality itself. At the Orion Bar, scientists test their ideas against nature, comparing equations and simulations to what truly happens when radiation meets matter. It is both a barrier and a window, an awe-inspiring reminder that, in the great struggle between light and shadow, radiation always wins. The Orion Nebula, one of the most beautiful and mysterious regions in the night sky, is being sculpted by a quiet, invisible force. This force does not shine like starlight, roar like stellar winds, or blast gas into chaos like ultraviolet radiation. It works in silence, yet without it, the Orion Nebula would look completely different. Perhaps it would not exist at all. This unseen artist is magnetism. Magnetic fields, though invisible and often forgotten, are one of the hidden architects of the universe. They don't make headlines like black holes or supernovae, but they are just as important. In places like Orion, where gravity, turbulence, and radiation are constantly colliding and twisting space, magnetic fields act as referees, trying to bring a kind of order to the cosmic brawl. They guide, resist, slow down, and redirect the wild motions of gas and dust, quietly deciding where stars are born and where space remains dark. But how do we even know that magnetic fields are there if we can't see them? Astronomers have found clever ways to reveal their presence. One of the most powerful tools is the study of polarized light. When light passes through or bounces off long, tiny grains of dust that are aligned with magnetic fields, it becomes polarized. Its electric field begins to favor a specific direction. By measuring this effect, scientists can map out the invisible magnetic lines threading through a nebula, just like how iron filings reveal the shape of a bar magnet. Special instruments such as SOFIA, the Stratospheric Observatory for Infrared Astronomy, and ALMA, the Atacama Large Millimeter Submillimeter Array, are used to capture this polarized light. What they see is stunning. In the Orion Nebula, magnetic field lines form elegant arching patterns that weave through glowing clouds of gas and wrap around dense clumps of matter. In some regions, these lines run alongside gas flows, helping the gas collapse into stars. In others, they cross against the flow, holding it back and creating regions of tension and balance that determine where stars can form and where they cannot. Magnetic fields can both help and hinder the birth of stars. Gravity pulls everything inward, trying to collapse giant clouds of gas into new suns. But magnetism can push back, adding a kind of invisible pressure that supports the cloud, like scaffolding holding up a crumbling wall. If the magnetic field is strong, it can delay or even stop star formation completely. If it is weak, gravity wins and the cloud collapses, lighting up new stars. In Orion, both outcomes can be seen side by side. Some areas are alive with new stars, jets, and glowing disks, while others, though equally dense, remain quiet and still. The difference often lies in the strength and alignment of the magnetic fields. These fields also play another crucial role. When a cloud of gas collapses to form a star, it begins to spin faster and faster, just like an ice skater pulling in their arms. But this spinning can't go on forever. Something must remove that extra spin, or the whole system would tear itself apart. Magnetic fields act as cosmic brakes, channeling angular momentum away through a process known as magnetic braking. Without this effect, planetary systems like our own could never form. Their spinning disks would become unstable and fly apart. Magnetic fields also help shape the dramatic twin jets that shoot out from young, forming stars. These jets are not just random bursts of gas. They are carefully directed outflows, focused and narrowed by twisted magnetic field lines. They act like cosmic plasma cannons, guiding streams of charged particles into space. The Orion Nebula is full of such jets, each carrying a magnetic signature written in light. Scientists studying Orion are also learning how magnetic fields and turbulence work together. In a place where gas and dust are constantly moving, colliding, and swirling, do magnetic fields get tangled up and weakened? Or does the chaos actually make them stronger? Some theories say turbulence destroys magnetic order, while others suggest it amplifies it, like a natural dynamo. Observations in Orion, especially around the Trapezium cluster and the famous Orion Bar, are helping astronomers test these ideas, turning theory into real understanding. The magnetic fields in Orion might not even be new. They could be ancient, perhaps millions or even billions of years old, remnants from earlier generations of stars or powerful supernova explosions. Over time, they have been stretched, twisted, and reshaped by the endless cycle of stellar birth and death. This shows that Orion is not just a glowing patch of gas. It is a living magnetic landscape where unseen forces decide what forms, what fades, and what stays still. We often focus on the dazzling colours of Orion's visible light, the reds, blues, and purples shining in photographs, but that's only the surface story. Hidden behind those bright veils is an entirely different world, one we can only see with infrared eyes. Infrared light can slip through thick clouds of dust, much like X-rays pass through skin. In regions like Orion, where most of the action is buried under gas and dust, infrared telescopes allow us to see the younger stars being born, the cold structures of gas that cradle them, and the faint warmth of dust heated by newborn suns. When we look at Orion through infrared light, it becomes a different universe altogether, a secret realm of forming stars, spinning disks, and magnetic storms. It is, quite literally, an infrared wonderland, where the invisible hand of magnetism continues to shape the stars of tomorrow in silence and light. When the Hubble Space Telescope first turned its sharp eyes toward the Orion Nebula, it revealed an incredible view in visible light, details no one had ever seen before. But when the Spitzer Space Telescope, and later the James Webb Space Telescope, JWST, looked at the same region using infrared light, something truly magical happened. A whole new world appeared. Hidden stars, once trapped inside dark clouds of dust and invisible to ordinary telescopes, suddenly came into view. Entire families of baby stars or protostars, some only a few thousand years old, began to glow on Spitzer's detectors. These were stars so young that they were still wrapped in their birth cocoons, slowly gathering mass from the gas around them. Infrared light lets us see what ordinary eyes cannot. It reveals stars in their earliest phases, Class 0 and Class 1 protostars, still buried beneath thick blankets of gas and dust. Their light is too weak to escape in visible wavelengths, but in infrared they shine softly, like embers under ashes. Some are so new that their surfaces are not even fully formed. Others spit out narrow streams of gas, twin jets, that shoot into space, visible only in certain infrared colours. These are stars in the process of being born, caught in the very act of creation. Infrared light also shows us something else, the dust itself. Instead of merely reflecting the light of nearby stars, the dust glows faintly with its own heat signature. This glow helps astronomers map the temperature and thickness of gas throughout the Orion Nebula. It shows where the gas is warm and collapsing, where it is cool and stable, and where powerful radiation has already cleared the way, leaving behind empty pockets of space. What once looked like a fog now appears as a delicate web, filaments of warmth, knots of pressure, and hollow bubbles of light. Among the most fascinating sights revealed by infrared observations are the protoplanetary disks, the swirling disks of gas and dust that surround young stars. In visible light they may appear as faint shadows or glowing rings, but in infrared their inner structure comes alive. We can see gaps, rings, and even spiral arms, all sculpted by the invisible hands of gravity and young planets forming within them. Some disks are thick and still building new worlds, others are thin and eroding under the radiation of nearby stars. By studying their glow, astronomers can tell how far along each system is in its journey from dust to planet. But the wonder doesn't stop there. Infrared light also uncovers the chemistry of creation. Certain molecules, such as water vapor, methane, carbon dioxide, and complex organic compounds known as polycyclic aromatic hydrocarbons, PAIDs, emit light only in the infrared. These glowing fingerprints tell scientists that the building blocks of life exist right in the heart of Orion. With infrared spectroscopy, researchers can not only identify these molecules, but also measure their temperature, speed, and location, building a detailed picture of how stars and planets are born from cosmic dust. The James Webb Space Telescope has taken this exploration to a new level. Its powerful mid-infrared instrument, MIRI, and near-infrared camera, NIRCam, have revealed details so fine that astronomers can now see jets, shocks, and newborn stars in areas once too dusty to penetrate. Even possible rogue planets, worlds drifting alone without stars, have begun to emerge from the shadows. The telescope's precision is so high that scientists can track small changes in young stars over short periods of time, watching as bursts of gas, flickering shadows, or sudden brightening events reveal the chaotic activity inside these growing systems. Yet perhaps the greatest gift of infrared astronomy is that it allows us to witness the birth of suns like our own. The Orion Nebula, bright enough to be seen with the naked eye, is more than just a beautiful cloud. It is a living nursery of creation. Within its folds lie the tiny trembling sparks of heat that may one day become planets, oceans, and maybe even life itself. When winds clash inside the Orion Nebula, new stars are not born quietly. Their arrival is loud and wild, like newborns screaming into existence, kicking and hurling gas at incredible speeds. The Orion Nebula is filled with these violent outbursts, and one of its most famous traits is the collection of shockwaves and bow shocks that scar its glowing face. These fiery marks are made when powerful stellar winds crash into their surroundings at supersonic speeds, writing fuzzy, glowing poems across the sky in the form of arcs, ribbons, and streaks of light. But what are we really seeing in these strange, shimmering shapes? When young stars form, especially those still feeding on the gas and dust around them, they don't just shine softly. They shoot out enormous streams of gas, not gentle breezes, but supersonic jets that race through space at hundreds of kilometers per second. As these jets smash into the surrounding nebula, they compress and heat the gas in their path, creating glowing shock fronts. The shocks are so powerful that they strip electrons from atoms, making the gas emit light in very specific colors, especially in visible and infrared light, such as hydrogen alpha red and the eerie green of forbidden oxygen. This is why the Orion Nebula sparkles with arcs, filaments, and wisps of color that look like fragments of some celestial storm. Among the most fascinating of these structures are the bow shocks, bent comet-shaped arcs that form when the wind from a fast-moving star collides with slower gas around it. A star moving swiftly through the nebula leaves a trail of light behind, just as a speeding boat carves a bow wave across water. These glowing waves often appear before a star changes direction, or before a newborn star begins shooting out jets of gas. They are clear signs of stellar activity, proof that Orion's nursery is very much alive. These shock waves are everywhere. High-resolution images from the Hubble Space Telescope, the James Webb Space Telescope, and powerful observatories on Earth reveal hundreds of them, some faint and delicate, others stretching across whole light-years of space. Many are directly connected to known jets or outflows from baby stars, while others remain mysterious, their sources long gone or buried deep within clouds of dust. Each of these shocks tells a story. By studying their brightness, shape, and speed, astronomers can learn how fast a star's wind is blowing, how dense the surrounding gas is, and even how long ago the outflow occurred. Some bow shocks appear layered or stacked, hinting that the young star ejected material in bursts, like cosmic hiccups. Others are tilted or split, showing how magnetic fields and gravity twist and reshape the paths of these jets as they move through space. In some parts of Orion, the violence reaches a new level. Shock waves collide with other shocks, and multiple stellar winds crash together, creating tangled knots of hot, compressed gas. These regions can be incredibly chaotic. One of the most famous is the BNKL region, home to the so-called Orion fingers. Scientists believe these long finger-like jets were created by a stellar explosion, or a close encounter, when several young stars either merged or scattered violently, throwing out streams of gas in every direction. This area, sometimes called the Orion outflow, contains narrow jets and bow shocks stretching for many light years, all pointing back to one explosive event. It's a vivid reminder that even the birth of stars can come with sudden and furious bursts of destruction. Shock waves do more than just tear things apart, they also build. When a star's jet crashes into nearby gas, the shock it creates can ripple back toward the star, changing the shape of its planet-forming disk. In this way, shocks might influence how planets are born. When these waves hit dense pockets of gas, they can squeeze them tight enough to start a new collapse, lighting the spark for the next generation of stars. So these shocks are both destroyers and creators, sculpting the nebula and keeping it alive, dynamic and ever-changing. From a scientific point of view, these cosmic shock waves are natural laboratories for studying how matter behaves under extreme conditions, things we can't reproduce on Earth. The enormous changes in pressure, temperature and density inside a bow shock reveal how plasma moves, cools, and flows in space. Every glowing arc is a real-time test of physics on a scale larger than anything we can build. Even more fascinating is that some of these shock structures change within a single human lifetime. Astronomers have seen certain waves shift and brighten over only a few decades. By comparing images from Hubble and James Webb taken years apart, scientists can actually track these waves as they move, like watching ripples travel across a cosmic ocean. It's a reminder that even though the universe seems timeless, parts of it are changing before our very eyes. At the very beginning of its life, a star is anything but calm. A newborn star, known as a protostar, doesn't just quietly glow while it gathers gas and dust. It fights back against the universe around it. It shouts into the darkness through two thin, blazing pathways of energy and gas that blast out in opposite directions. These are called bipolar outflows, two powerful jets of gas shooting away from the poles of a forming star. Their presence is one of the clearest signs that something great and fiery is about to be born. In the Orion Nebula, these outflows are everywhere. They stretch across distances so vast that they cover several light years, like cosmic flamethrowers cutting tunnels through the surrounding gas. Each one leaves behind glowing trails, beautiful scars that mark the raw power of creation. Some of these jets are faint and can only be seen with infrared light, while others blaze like lightning across the nebula, tearing through space in bright arcs of shock-heated material. The question is, what causes such incredible twin streams of force? It all begins with the protostar itself, a thick, glowing ball of gas still pulling matter from a swirling disk that orbits it. This disk spins rapidly, feeding the young star at its center, but the gas falling in brings with it something more than mass. It carries rotational energy. The forming star can't absorb all of this spinning force at once. The extra energy needs an escape route, and this is where magnetic fields take control. As the disk spins, it twists the magnetic field lines into a spiraling corkscrew shape. These twisted lines act like launching rails, flinging streams of gas out from the star's poles in narrow focused jets. These jets move at speeds of hundreds of kilometers per second, carrying with them enormous amounts of matter, energy and momentum. As they crash through the surrounding cloud, they create shock waves that heat up the gas, making it glow like neon in the dark. The result is a stunning bipolar outflow, often shaped by bow shocks at its leading edges, and sometimes bright enough to trace all the way back to the young star that fired it. Some of the most famous examples in the Orion Nebula are Herbig-Haro objects, such as HH 212 and HH 34, glowing marks where these jets have slammed into surrounding clouds. These outflows can last for tens of thousands of years, fading and flaring again as the amount of gas feeding the star changes over time. Often they don't flow steadily like a river. They pulse, bursting forth in sudden, powerful episodes, much like a machine gun firing in space. Each burst leaves behind a bright knot of gas, giving the jet a segmented, bead-like appearance. What's truly amazing is how precise these outflows can be. Even in the wild, chaotic environment of the Orion Nebula, many jets stay perfectly straight over enormous distances. This incredible stability is thought to come from the magnetic fields that surround the disk, acting like a nozzle that keeps the jet sharply focused. By studying these outflows, astronomers can actually map the invisible magnetic structures that shape young stars. But these jets aren't just dazzling light shows. They play an essential role in how stars are born. They act like safety valves, releasing excess energy and angular momentum so that the star doesn't spin apart or grow too fast. Without them, the star-forming process might collapse under its own chaos. In this way, the jets help the newborn star reach a stable, mature state. They also shape the world around them. By blasting out low-density paths through the nebula, these outflows clear space for future planets to form safely within surrounding disks. Yet they can also be destructive. If a jet happens to pass too close to another forming system, it might rip the delicate disk apart, ending that world's chance at becoming a solar system. In this way, jets act as both protectors and destroyers, sculpting the cosmic landscape with every burst. Modern telescopes such as the James Webb Space Telescope and ALMI have given astronomers an entirely new view of these mysterious jets. We can now see not only the gas being hurled into space, but also the dust that rides along within it, the molecules it carries, and even faint signs that the jets themselves are spinning, physically carrying angular momentum away from the star in a spiraling flow. These discoveries are helping scientists connect how stars form, how their disks behave, and how the first building blocks of planets take shape. Bipolar outflows also serve as cosmic clocks. By measuring the length of a jet and how fast it travels, astronomers can estimate when a star first began to grow rapidly and how long it has been shaping its surroundings. In Orion, some of these outflows stretch across several light years, showing that they've been active for thousands of years, while others are short and young, marking stars that have only just begun to breathe fire. Every jet tells a story of struggle, energy, and creation. It says, "I am here. "I am being born, and I will not go quietly." And sometimes, these acts of violence do more than give life to a single star. They reshape the entire neighborhood. The blast fronts from these outflows can push down on nearby clouds, compressing them until gravity takes over and new stars begin to form. This is the next great step in the chain of creation, triggered star formation. In places like the Orion Nebula, one generation of stars doesn't just appear, it provokes the next. The powerful winds, radiation, and shock waves from massive young stars act like both midwives and arsonists, destroying some regions while igniting others. When a giant star forms, like those in Orion's famous Trapezium cluster, it unleashes enormous ultraviolet light, fast winds, and waves of pressure that sweep through the nebula. These forces carve out hollow spaces, tear down towering pillars of gas, and illuminate the surrounding clouds in glowing colours. Behind the destruction, though, they leave behind pockets of dense, squeezed gas. When these pockets reach a critical point, they collapse under their own weight, and a new star is born. When one generation of stars finishes its work, it often leaves behind powerful energy that changes the space around it. That energy can make nearby gas clouds thicker and denser, setting the stage for new stars to form. It's almost as if the older stars are passing a torch forward, using light, wind, and shock to spark the next generation into life. This chain reaction works especially well in the Orion Nebula, a glowing, chaotic workshop of creation. Everywhere we look in Orion, we can see signs of this cosmic relay. There are bright-edged clouds, twisted filaments of gas that look like glowing ropes, and vast arcs of light where waves of pressure have slammed into older clouds. These glowing structures are evidence that shock fronts, waves of energy pushed outward by powerful stars, have hit the gas already floating in the region. In many of these places, small clusters of infant stars or protostars can be seen forming just behind the expanding walls of radiation, as if they were born in the quiet that follows a cosmic storm. One of the clearest examples of this happens along the famous Orion Bar, that sharp, glowing edge we spoke about before. Behind this dazzling boundary lies a compressed layer of gas, where astronomers have found many young stars still wrapped in their birth cocoons. These stars appear to be much younger than the ones in the Trapezium cluster, suggesting that the radiation from the older, brighter stars might have triggered their birth. It's not absolute proof, but it's a very strong clue, a whisper from the nebula that one generation has given rise to another. Just below the Trapezium cluster lies another remarkable area called Orion South. Here, astronomers have seen evidence of expanding bubbles of ionized gas, racing outward and crashing into denser clouds nearby. Inside those clouds are more protostars, just beginning to glow. The layout of this region makes the cause and effect hard to ignore. It's as if the massive stars in the centre sent out shock waves that struck the gas and set it ablaze, igniting new suns in their path. This makes the Orion Nebula look less like a single event and more like a grand, continuous performance. Star formation here doesn't seem to happen all at once, but in a chain, with each generation born a little later and a little farther from the centre than the last, like ripples spreading across a pond. The story stretches back millions of years, and while we can't watch it unfold in real time, the pattern is written all over the nebula's shape and light. But this triggered star formation is not guaranteed. It's a delicate balance, almost like trying to light a fire in a storm. If the shock wave from an older star is too weak, it won't squeeze the gas enough for it to collapse into a new star. If it's too strong, it can tear the gas apart completely, scattering it before gravity can take hold. Everything has to be just right. The gas must be dense enough to press inward, cool enough to stay together, and steady enough to resist being blown away. Astronomers test these ideas with powerful telescopes that capture high-resolution images and detailed spectra. By studying how fast the gas moves, how hot it is, and how dense it becomes in certain regions, they can tell whether a cloud is collapsing under its own gravity or being pushed by outside pressure. In Orion, many of these dense pockets show signs that they are being compressed from the outside, supporting the idea that older stars are indeed triggering new ones. This process doesn't just explain how stars are born, it also shapes the entire structure of the nebula. Long chains of stars, graceful arcs of light, and filaments stretching like glowing rivers all owe their existence to this cycle. It even decides how long the nebula stays active. Massive stars live short, fierce lives, only a few million years, but when they explode as supernovae, they can send out one last wave of creation before the gas finally spreads out and the region falls silent. It's a cosmic relay race that never truly ends. Each generation runs for a while, blazing brilliantly, then hands its energy to the next before fading into dust. Orion shows us that stars don't form in isolation. They are born together, in waves and generations, connected by the breath and fury of those that came before. Far from being peaceful or solitary, the birth of stars is a story of inheritance, violence, and beauty. A grand, fiery conversation between the past and the future of the universe. Before the stars of the Orion Nebula light up and send out their fierce jets, there is a deep, hushed silence. A silence not empty, but filled with the most common and quiet material in the universe, molecular hydrogen. This simple molecule, made of two hydrogen atoms bonded together, is the raw material of stars. It hides everywhere in Orion, but it cannot be seen with ordinary eyes. It doesn't burn or glow like charged hydrogen. Instead, it whispers faintly in the infrared, marking the coldest and darkest corners of the great stellar nursery. Molecular hydrogen, or H2, forms in the still, cold regions of space, where gas gathers thickly and where the violent ultraviolet light of nearby stars cannot reach. These areas are freezing, just a few dozen degrees above absolute zero, and yet, in their stillness, life stirs. When something disturbs them, such as a passing shockwave, a burst of stellar wind, or the force of a newborn star's jet, the hydrogen begins to glow softly. Its light is not bright or colourful to the eye. It shines in delicate, specific wavelengths of infrared, like invisible fingerprints hidden in the cosmic mist. With instruments such as those aboard Spitzer, ALMA, and the mighty James Webb Space Telescope, astronomers can detect this faint glow and draw maps of Orion's coldest and most mysterious regions. It's like switching on night vision in what once seemed an empty room. Suddenly you realise there's movement everywhere. The nebula reveals a hidden face. Instead of the glowing arcs and fiery clouds seen in Hubble's images, the molecular hydrogen shows us thin filaments, faint veins, and small pockets where stars are quietly being born. These places do not shine because they are hot. They glow because something has made the hydrogen molecules shake and sing, releasing tiny bursts of light known as photons. Through these maps, scientists have discovered that what once looked like dark space between bright stars is actually a vast web of cold gas, stretching for light years and woven together like threads of a gigantic cosmic spider web. Many of these threads lead straight into thick clusters where new stars are forming, showing the hidden paths that gravity uses to gather gas into the seeds of suns. In this way, the soft glow of hydrogen doesn't just show us where stars are, it shows us how they are made. One of the most astonishing things about molecular hydrogen is how it can trace the paths of powerful outflows. When a young star sends out jets, the gas around it gets shocked and heated, and the hydrogen responds by lighting up in graceful arcs and bright spots of infrared light. It marks the trail of the jet like a contrail left behind by an airplane. In places like the famous BNKL outflow, these glowing arcs and knots are the remains of violent explosions that happened only a few thousand years ago, mere moments in cosmic time. Each shimmering patch of hydrogen is like a footprint left in gas, a timestamp of motion frozen in light. But molecular hydrogen is more than just a witness to these cosmic events. It's also a kind of cosmic gatekeeper. The amount and condition of hydrogen decide where stars can form and where they cannot. If there's enough hydrogen, and if it's cold and calm enough, gravity can pull it together to form a new protostar. But if the gas is too warm or too turbulent, the process fails. So, by measuring how much molecular hydrogen exists in each region, astronomers can almost predict where new stars will soon appear. It's like a weather forecast for the universe, built not from clouds and rain, but from the faint whispers of infrared light. However, molecular hydrogen is extremely shy. It's difficult to observe directly because it doesn't easily emit light. The molecule is too symmetrical to glow on its own. It needs a strong push, such as shocks or bursts of ultraviolet light. That's why astronomers often search for indirect clues, especially a faint line at about 2.12 microns in the near-infrared. When these rare conditions occur, hydrogen seems to awaken, glowing beautifully in the turbulent landscapes of Orion. Now, with the incredible power of the James Webb Space Telescope, Astronomers are seeing this hidden world in more detail than ever before. Webb's sensitivity allows it to detect hydrogen in tiny filaments, in the densest prestellar cores, and even inside the swirling disks that may someday form planets. In the Orion Nebula, Webb has already revealed dozens of new jets, faint outflows, and small, unseen protostars hiding in the dust, an entire secret population that was invisible until now. And yet, molecular hydrogen is not just part of the beginning, it's also part of the end. It's the first to gather when a cloud starts forming a star, and the last to remain after the star dies. Long after a supernova has torn a cloud apart, the leftover fragments cool and slowly turn back into quiet hydrogen once again, drifting through space and joining new clouds. It's as if hydrogen remembers. It is the ghost of past stars, the breath before the scream. Among this hydrogen drift the tiniest seeds of all worlds, dust grains. You can't see them. They're smaller than smoke particles, lighter than ash. Yet these grains are some of the most important things in the Orion Nebula. They move silently through the chaos of gas and radiation, clumping together to form the solid bones of future planets, moons, and comets. They are the first step from chaos to creation. These dust grains are made of silicates, carbon, iron, and ice, depending on how and where they were formed. Many of them were born in the last breaths of dying stars, red giants and exploding supernovae that lived and perished long before Orion's stars were born. Blown out into the galaxy, they became the ancient building blocks of new worlds. Every speck of dust in Orion is, in a way, a fragment of another age, a tiny relic of an earlier universe. But in Orion, even dust is not safe. The fierce ultraviolet light from the Trapezium cluster slams into these fragile grains, heating them, stripping them apart, or sometimes destroying them completely. Some of the dust glows warmly from the energy it absorbs, radiating in the mid-infrared and painting Orion in fiery colours we cannot see. In other areas, dust acts as a shield, protecting the cold hydrogen behind it from destruction. Without dust, the universe would be a very different place. Molecular hydrogen, the most common molecule in space, cannot even form without it. Dust grains act like tiny meeting points where hydrogen atoms can join together. Without these small solid surfaces, hydrogen would stay separate, and the gas would remain far too hot to clump together. Dust cools space by releasing heat, allowing clouds of gas to collapse and give birth to stars. And without dust, there would be no planets, no worlds at all, because planets are born from dust. Around young stars in thick spinning disks called protoplanetary disks, the story of planets begins. Inside these disks, fine grains of dust, smaller than the width of a human hair, start to bump into one another. At first, they collide softly, sticking together through gentle electrostatic attraction, the same force that makes a balloon stick to your hair. As time goes on, these tiny grains become larger clumps, turning into pebbles, then into rocks, and finally into massive bodies called planetesimals, objects several kilometers wide that can pull in even more material using their growing gravity. From these humble beginnings, whole planets eventually emerge, but in the Orion Nebula, that process is anything but easy. In calmer regions of space, a dust grain might survive for millions of years, drifting peacefully and slowly growing in size. In Orion, however, things are much harsher. The region is filled with intense radiation from massive hot O-type stars. A dust grain too close to one of these blazing giants could be vaporized in just a few thousand years. Because of this, location means everything. Protoplanetary disks near the bright cluster of the Trapezium stars often get stripped away, their outer parts burned and eroded by fierce ultraviolet light. Those that are farther from the center of the nebula live quieter lives. They are larger, cooler, and have a better chance of surviving long enough to form full planetary systems. Thanks to modern telescopes such as ALMA and the James Webb Space Telescope, astronomers can now see these fragile beginnings with amazing detail. Using infrared and submillimeter light, they can measure the size, temperature, and spread of dust grains in Orion. They have found everything, from incredibly fine particles smaller than a micron to pebbles several millimeters across, and even signs that some grains are already growing inside these protoplanetary disks. This is clear, direct proof that even in this harsh and violent environment, the first steps toward creating new worlds are happening right now. Dust also changes how we see the Orion Nebula itself. Those dark, shadowy lines and patches in Hubble's pictures are lanes of dust that block and scatter light. They are what make the bright stars near the nebula appear redder, because dust absorbs blue light more strongly. The famous colourful glow of Orion is partly caused by dust grains absorbing starlight and then shining it back out again in softer, warmer tones. And not all dust is the same. Some grains contain complex carbon molecules, including long chains known as polycyclic aromatic hydrocarbons, molecules that could be early steps toward life's chemistry. These carbon-rich grains glow under ultraviolet light, and their unique fingerprints have been detected all across Orion. It is possible that the first ingredients for life begin not on planets, but in clouds of dust like these. There is even growing evidence that comet-like objects may form while the dust is still surrounded by thick gas. These icy primitive bodies could one day carry water and organic molecules to young rocky planets, the very materials that make oceans and atmospheres possible. In the Orion Nebula, we may be witnessing the earliest moments of that process as tiny icy seeds start gathering the stuff of life itself. The Orion Nebula may look like a glowing garden of fire and light, but its true heart is not made of heat. Beneath its shining surface, under clouds of burning gas and bright newborn stars, lies a cold and invisible world, a vast ocean of molecular gas and dust. This dark material, though frigid enough to swallow light, holds the secret power to create stars. It is the hidden engine that keeps the nebula alive. Astronomers who study Orion do not search for things that sparkle. Instead, they listen for things that whisper. And one of the most important voices in that whispering dark belongs to a simple molecule called carbon monoxide, or CO. It is made from only one carbon atom and one oxygen atom. Such a small and simple thing, yet one of the most valuable clues in the entire cosmos. You might expect something so tiny to be unimportant, but carbon monoxide is one of the best ways to find molecular hydrogen, or H2, which is the raw material that makes stars. The problem is, hydrogen molecules are almost invisible. Even though they are the most common molecules in the universe, they rarely shine at the low temperatures found in star-making clouds. But CO, on the other hand, glows beautifully at radio and submillimeter wavelengths. When gas clouds cool down to between 10 and 30 degrees above absolute zero, that is, between 10 and 30 Kelvin, CO molecules begin to twist and spin, releasing faint pulses of energy. These gentle signals can be detected at a very specific frequency, around 115 GHz. Telescopes such as ALMA, IRAM, and JCMT are tuned precisely to these frequencies. They collect the soft light of carbon monoxide and turn what would otherwise be total darkness into glowing, detailed maps showing how the cold gas moves, how dense it is, and how it is shaped. In the Great Orion Molecular Cloud Complex, these carbon monoxide surveys have changed everything we know about the region. What looks to our eyes like a single bright patch of sky is, in truth, part of a giant interconnected system that stretches more than 240 light-years across. It is filled with threads, bubbles, knots, and dense hearts of gas, the true structure of the beast beneath the beauty. By mapping CO, astronomers can trace the filaments of thick gas where new stars are forming. They can see the bubbles and hollow spaces carved out by powerful stellar winds and ancient explosions. They can follow the motions of gas moving toward or away from us, and identify the heavy clumps that are about to collapse into new stars or even whole clusters. In Orion, these CO maps reveal enormous regions called Orion A and Orion B, immense clouds overflowing with the raw materials of creation. They show how massive stars, such as those in the Trapezium cluster, have blasted holes and tunnels through the surrounding gas, pushing it into bright ridges where the next generation of stars may already be forming. But CO maps are more than pictures, they are time machines. By studying small shifts in the frequencies of CO light, scientists can measure how fast the gas is moving and in what direction. This allows them to rebuild a three-dimensional model of the nebula. They can tell whether stars that seem close together are actually neighbours, or only appear so by chance. They can watch filaments fall inward, spin like whirlpools, or spread apart. Sometimes these maps even reveal hidden drama. In many places, the CO signal shows signs of violent outflows, twin jets of gas shot out by newborn stars. As these jets plough through the cloud, they drag CO molecules along, leaving bright streaks of motion that mark where invisible protostars are hiding. Even when the stars themselves are buried too deep to see, the restless CO around them betrays their presence. There are also regions where CO simply vanishes. In the coldest, densest pockets, the ones that are just about to give birth to new stars, CO freezes onto dust grains, disappearing from the gas. This chemical silence tells astronomers that a core is on the edge of collapse. The absence of CO, ironically, becomes a sign of creation. When scientists combine CO maps with infrared and visible images, they peel back the layers of the nebula like the skin of an onion. Visible light shows the shining surface, the skin. Infrared light reveals the dust-hidden interior, the flesh. But CO shows the skeleton, the bones, veins, and arteries of the cloud, the framework that holds it all together. Thanks to massive surveys from telescopes like Nanten, F-Grau, and the ultra-detailed views from ALMA, astronomers now understand that Orion is not just a place of starbirth. It is a living, breathing system, a network of flows, filaments, explosions, and rebirth. Carbon monoxide, the simplest of molecules, is the language through which this hidden world speaks. When people think about outer space, they rarely think about chemistry connected to life. But deep inside the Great Orion Nebula, something strange and beautiful is happening. Hidden among the glowing gas, the shock waves, and the falling clouds of matter, there are tiny, complex molecules quietly catching ultraviolet light from nearby stars and re-emitting it as a soft glow. These are not the raw ingredients that make stars. They are far more intricate. They're called polycyclic aromatic hydrocarbons, or PALATs for short. You can imagine PALATs as flat rings made of carbon, sometimes with bits of hydrogen attached. Tiny, cosmic versions of the carbon rings found in soot or on the burnt edges of toast. But instead of being trapped in smoke or dust here on Earth, these delicate molecules drift freely through the interstellar medium of Orion, floating on dust grains in a harsh ocean of radiation. When ultraviolet photons from young, hot stars, especially those in the famous Trapezium cluster, hit these carbon rings, they react by glowing softly in infrared light. This gentle glow, known as fluorescence, gives them away to astronomers. In fact, many of the shimmering, colourful regions seen in infrared images of the Orion Nebula are bright because of pHs. Space telescopes such as Spitzer, ISO, and the James Webb Space Telescope, JWST, detect these glowing signals at wavelengths of about 3.3, 6.2, 7.7, 8.6, and 11.3 microns. These particular wavelengths, known as aromatic infrared bands, act like glowing signs in the cosmic fog, showing astronomers exactly where complex chemistry is happening, even when the molecules themselves are invisible. What makes this even more amazing is that PAs are organic molecules. They are built from carbon and hydrogen, arranged in complicated structures that are surprisingly difficult to make even under Earth's conditions, let alone in the violent chaos of a star-forming nebula. Yet, there they are, shining in one of the most active and turbulent regions of our galaxy. Their presence shows that the universe begins making complex molecules long before stars, planets, or even stable disks of matter come into being. In Orion, PAS tend to gather along the borders of cold molecular clouds, in special regions known as photodissociation fronts. These are thin zones where the fierce ultraviolet light from young stars just starts to eat into the surrounding gas. It is a delicate balance, strong enough to break apart simple molecules, but not so strong that it completely destroys the fragile organic ones. This narrow twilight zone between light and dark is where PAs thrive. Their existence is not just interesting, it is crucial. First, PAs help regulate the nebula's energy. They absorb harsh ultraviolet radiation and release it again as gentle infrared light, helping to cool the surrounding gas and maintain the fragile balance needed for new stars to form. Without them, the region might become too hot and unstable for stars to grow properly. Second, these molecules could be the stepping stones toward life itself. In laboratory experiments and meteorite samples, pairs have been seen combining with other molecules to form amino acids, nucleic bases, and other prebiotic compounds, the very building blocks of life. If they can survive the radiation and chaos of the Orion Nebula, then they could easily travel on dust grains into protoplanetary disks and later onto newborn planets. In that sense, Orion is not just a nursery for stars, it might also be a garden planting the seeds of life across the galaxy. Third, Paths give astronomers an extraordinary way to trace the hidden structure of the nebula. Because they glow only in certain conditions, where hot gas meets cold, they outline the edges of radiation fronts, filaments, and hollow cavities. By mapping where these glows appear, scientists can see where massive stars are reshaping their environment and stirring up the chemistry of space. However, peaks are not immortal. If they are exposed to too much ultraviolet radiation, they break apart, especially the smaller ones with fewer carbon atoms. So the spread of PAHs across Orion also tells a story of violence and survival. Calm, shielded areas still contain them in abundance, while places blasted by fierce radiation or stellar winds are almost empty. The delicate molecules destroyed or carried away. The James Webb Space Telescope now provides the clearest and most detailed view of these carbon rings ever seen. With its powerful instruments, JWST can not only detect PAHs, but also tell how their structures vary from place to place, revealing how the nebula's chemistry evolves over time. In the heart of this blazing cloud, where stars are born out of storms of fire and gas, something fragile and unexpectedly familiar endures. Carbon rings, glowing softly, drift across the light, whispering of what might someday become life. They are small, but they are strong. They are the seeds of possibility, tiny, shining messengers moving through Orion, carrying the chemical promise of worlds yet to come. And even as their faint light reaches Earth, it passes through strange, half-transparent layers of dust and gas, bending and scattering before it meets our eyes. That shimmer reminds us that the Orion Nebula is not just a simple cloud of light. It is a layered, living structure, full of mystery, chemistry, and the quiet beginnings of creation itself. The Orion Nebula shines brightly in the sky, but its beauty hides a secret. What we see is not the whole story. Between us and that glowing cloud of gas lies a thin, almost invisible layer of dust, a veil so faint that it is easy to overlook. This veil is not truly part of the bright cloud itself, yet it is still tied to it, like a ghostly echo of its outer edge. The light that finally reaches Earth has already passed through this dusty curtain, being softened, dimmed, and slightly bent along the way. At first, astronomers thought this veil was nothing special, just another layer of ionized gas. But later they discovered that it was much more than that. It was a mask that revealed the hidden shapes of what lies deeper inside the nebula. The first hints came from something strange. The brightness of Orion didn't match what scientists expected. Some areas looked too dim, while others appeared oddly shifted toward red or blue light. When they studied the nebula more closely using spectroscopy and light polarization, the truth became clear. There was a delicate, uneven sheet of interstellar dust floating between us and the nebula's heart, like a fogged window between you and a glowing neon sign. This veil doesn't block the light completely. Instead, it filters it in beautiful and complex ways. The tiny dust grains absorb some colors, scatter others, and let the rest pass through. Shorter wavelengths, like blue and violet, get scattered the most, while longer ones, like red and infrared, pass through more easily. That's why many of the stars around Orion look redder than they really are. Astronomers call this effect interstellar extinction. By studying how the light of different colors is dimmed, they can measure how thick the veil is, what it's made of, and how it is shaped. The veil itself is far from smooth. It ripples, folds, and clumps together in strange and graceful patterns. In some places it is only a few light months thick, while in others it stretches across several light years. These ripples are not random. They are sculpted by the same cosmic forces that shape the nebula behind them. The push of radiation, the pressure of stellar winds, and the pull of gravity. In some regions, the expanding wave of ionized gas from Orion crashes into the veil, creating a thin border where hot and cold gases meet and swirl together. The veil is not static either. In some spots, young stars have pierced holes through it with their jets and outflows, carving tunnels where astronomers can peek more deeply into the glowing heart of Orion. Other areas are so dense that even infrared light cannot pass through, hiding entire clusters of newborn stars that can only be seen in radio or mid-infrared wavelengths. In this way, the veil acts as both an obstacle and a gift, hiding some secrets while revealing others, depending on how and where we look. But perhaps the most important thing about the veil is what it teaches us about Orion's true shape. When we look at images of the nebula, they appear flat, like paintings spread across the night sky. Yet the veil helps astronomers see it in 3 dimensions. By measuring how much dust lies in front of or behind different regions, scientists can figure out which parts are closer and which are farther away. Some of the wisps of gas once thought to be inside the main glowing cloud are now known to sit in front of it, casting long shadows like smoke drifting between a fire and a camera lens. Because of this discovery, the Orion Nebula is no longer seen as a flat picture of glowing gas, but as a vast, layered sculpture, a cosmic landscape filled with thick filaments, shining arcs, hollowed-out cavities, and a translucent veil that shifts the way we see everything. It is as though the nebula wears a mask, one that must be lifted layer by layer to reveal its true depth. The newest observations from the James Webb Space Telescope are peeling that mask even further. Its powerful infrared vision has revealed fine patterns within the veil, thin streamers of dust, delicate waves of polarized light, and magnetic fields twisting through the mist. These discoveries suggest that the veil is not just a passive layer of dust, but part of a much larger magnetic structure, possibly linked to the great Orion-Eridanus superbubble, an enormous shell of gas and dust that stretches for hundreds of light years behind the nebula. Step back for a moment from the bright, stormy heart of the Orion Nebula and take a wider look, not just a little wider, but hundreds of light years wider. Surrounding the glowing clouds of Orion is an enormous, nearly invisible ring of hot gas that stretches across space like the fading ripples left behind by some ancient cosmic explosion. This vast structure is known as the Orion-Eridanus superbubble. It is not simply a beautiful backdrop for the Orion Nebula. It is the grand stage on which the entire region's history has been written and continues to unfold. The superbubble is a gigantic hollow cavity in the interstellar medium, filled with thin, superheated plasma. It stretches from the constellation of Orion all the way into the neighbouring constellation of Eridanus, covering an astonishing distance of about 1,200 light-years across. To grasp its scale, imagine that the brilliant Orion Nebula itself, so large and dazzling when seen through telescopes, sits tucked near the bubble's edge like a single glowing spark inside the rim of a charred crater. But how did this immense cosmic hollow come to exist? The most likely answer is supernovae, and not just one. Over the past 10 to 15 million years, many massive stars belonging to Orion's older stellar groups, such as Orion OB1A and Orion OB1b, have burned through their short lives, exploded as supernovae, and blasted enormous amounts of energy into space. Each explosion sent out powerful shockwaves that swept up gas and dust, carving out an ever-growing cavity. Together, these repeated bursts of destruction created the superbubble we see today, a vast, low-density interior filled with hot plasma, surrounded by a thicker outer shell of compressed material. Though faint, the bubble still glows softly in X-rays, radio waves, and ultraviolet light. One of its most striking visible traces is Barnard's Loop, a great red arc that curves across the eastern side of Orion, like a glowing halo around the nebula. Yet this magnificent structure is not frozen in time. It is still expanding, though now much more slowly. Its outward motion continues to interact with the nearby Orion molecular cloud complex, pressing on some areas, dispersing others, and helping to shape where new stars are forming even today. In a sense, the superbubble might have helped to create the very stars of the Orion Nebula by triggering their birth through compression of cold gas. It forms part of a grand feedback cycle that spans millions of years and hundreds of light years, where the death of one generation of stars ignites the birth of the next. Astronomers have studied this bubble not only through images, but also by measuring the motion of its gas. Using observations of carbon monoxide and hydrogen alpha emission lines, they can see clear signs that the gas is moving outward. Gas on one side is coming toward us, while gas on the opposite side is moving away. The bubble's shape is not perfectly round. Instead, it resembles an open-ended shell, likely distorted by the influence of other nearby clouds and the structure of the Milky Way's disk. Even more fascinating, there is evidence that the superbubble has punched through part of the galactic disk, letting hot gas escape into the halo above the Milky Way. This process could be one of the ways galaxies recycle gas between their star-forming regions and their outer layers, an essential part of galactic evolution. That makes superbubbles like Orion-Eridanus not just local curiosities, but key players in the life story of galaxies themselves, And Orion's superbubble is not alone. The Milky Way is scattered with similar giant cavities, silent scars left behind by clusters of massive stars that lived fast and died violently. What makes the Orion-Eridanus superbubble special is its closeness to Earth, its high level of activity, and how well astronomers have been able to study it. It gives us a front-row seat to the cycle of stellar death and rebirth, all happening within a single connected region of space. There are signs that new superbubbles may already be forming inside the old one. Some of the Trapezium cluster's largest stars, such as Theta 2 Orionis C, are expected to go supernova within the next few million years. When they do, their explosions will send even more energy racing through the region, layering new shockwaves over old ones and reshaping the structure of the bubble once again. When stars are born, they do not come quietly into existence. They arrive with fury and motion, sending out great jets of gas that pierce through the surrounding darkness like cosmic lances. These newborn stars, still hidden inside clouds of dust and gas, throw out streams of matter at astonishing speeds, hundreds of kilometers every single second. These jets are already among the most dramatic sights in astronomy. But now imagine if those jets, those immense beams of gas and energy, were not simply going straight but were spinning. A tiny twist, a rotation. It might not sound like a big deal, just a small twist in a giant stream. Yet that simple twist could unlock one of the great secrets of how stars and even planets are born. The Orion Nebula, that beautiful glowing cloud hanging in the sword of the constellation Orion, is a perfect place to look for answers. It's a busy nursery of creation, filled with baby stars, astronomers call them protostars, still forming inside thick envelopes of gas and dust. And all around them are these incredible jets, narrow and bright, stretching across space like cosmic arrows. You can see them in visible light, but also in infrared light that passes through dust. They appear as thin streaks marked with glowing spots and shock fronts. Those are areas where the fast-moving gas collides with slower material, lighting up in response. But if you look more closely, you start to notice something strange. These jets are not all the same. Some seem uneven, slightly tilted or twisted. Others look like they're curving, forming delicate corkscrew shapes as they move outward. And in a few very special cases, astronomers have found real evidence that these jets are actually spinning as they blast out into space. Why does that matter? Because in astronomy, rotation, the act of spinning, is everything. It shapes how stars form, how planets appear, and how entire solar systems organize themselves. Think of a figure skater on the ice. When she stretches her arms out, she spins slowly. But when she pulls her arms close to her body, she spins faster. The reason is a physical rule called the law of conservation of angular momentum. The same rule applies in space. When a huge cloud of gas and dust starts to collapse under its own gravity to form a star, it begins to spin faster and faster as it gets smaller. The shrinking makes the rotation speed increase, just like the skater pulling in her arms. But there's a big problem. If the spinning keeps getting faster without anything to stop it, the forming star would tear itself apart before it could fully take shape. There needs to be some way to get rid of that extra spin, to release that excess rotational energy, or the star simply won't form properly. This is where jets come in. For a long time, astronomers suspected that these narrow, powerful jets might not just be beautiful side effects of star formation, but essential tools of balance. Cosmic exhaust valves that let the forming star shed its extra spin safely into space. Theoretical models suggest that jets are launched by magnetocentrifugal forces, a mouthful of a word that means magnetic fields are doing the heavy lifting. Imagine invisible magnetic field lines wrapping around the young star or its surrounding disk of gas. These lines act like taut springs, flinging material outward along the star's axis of rotation. If that is true, then those magnetic jets wouldn't just push matter away, they would also carry away some of the system's spin. That means, logically, that the jets themselves should rotate. But proving that is very hard. You're trying to detect extremely tiny differences in speed across something that's only a few astronomical units wide. That's a few times the distance between the Earth and the Sun, while the object itself is hundreds or even thousands of light years away. It's like trying to see a spinning coin on the moon through a telescope. For decades, this was simply beyond our reach. But now, thanks to advanced instruments like the James Webb Space Telescope, often called JWST, and the Atacama Large Millimeter Submillimeter Array, known as ALMA, we finally have the resolution and sensitivity to see the faintest details, even the small twists in the light coming from these jets. And in the Orion Nebula, scientists have indeed begun to find that twist. By studying the Doppler shift, the tiny change in wavelength that happens when something moves toward or away from us, astronomers notice slight differences across the width of some jets. One of the best examples comes from a system known as Herbig-Haro object, number 212, or HH212 for short. This is a remarkably narrow and symmetrical bipolar jet, meaning it shoots out in two opposite directions from a central protostar, like the nozzles of a double-ended fountain. When astronomers looked closely, they saw that one side of the jet appeared to be moving slightly toward us, while the other side was moving slightly away. The difference was only a few kilometers per second, a small shift, but perfectly in line with what would happen if the jet was spinning around its own axis as it blasted into space. This discovery, though still debated among scientists, offers strong support for the idea that jets are not just outflows of material, but also key mechanisms for removing excess spin from young stars. They don't only eject mass, they also expel angular momentum, the rotational energy that must be shed for a star to form safely. If this process turns out to be common across most star-forming systems, it would explain a major mystery: why young stars do not spin nearly as fast as we would expect. Without some way to slow them down, newborn stars should be rotating at breakneck speeds, possibly fast enough to break apart, but they don't. Jet rotation may be the missing piece, a clean, physically sound answer to how stars regulate their spin during birth. Yet the implications go even further. These jets are not just straight beams of gas. If they truly twist and rotate, that means they may be structured, complex, and alive with motion. Some computer models suggest that rotating jets could create spiral shock waves as they plow through the surrounding gas. These spirals might even influence other nearby regions where new stars are forming, triggering or disturbing the process in neighbouring cores. In other words, a spinning jet might not just punch a tunnel through the cloud, it could carve a spiral pattern, shaping the landscape of star formation around it. Observations from Orion support this idea. Many jets there show strange patterns, bright knots that seem to break off like beads from a string, wavy trails that follow corkscrew paths, or twin jets from binary systems where each protostar sends out a flow that spins in the opposite direction of its partner. It's almost like watching a cosmic dance of light and motion, where every move tells part of the story of how stars balance their birth. These peculiar structures, the wiggles, the twists, the loops, could all be signs of rotation or magnetic instability. Each one offers a small but valuable clue, allowing scientists to compare what they see with what computer simulations predict. The amount and direction of spin that a young star ejects could shape the evolution of its surrounding disk, the disk where planets will one day form. If jets remove too much spin, the disk might shrink too quickly, leaving less material for planets. If they remove too little, the disk might become unstable and break apart. In multiple star systems, the way jets twist and interact could even influence the final layout, whether stars end up close together, far apart, or with planets in tilted orbits.